Okay, good morning. Hello. Yeah, we have significantly less people today in the morning. So, because the party yesterday was, I think, quite good. So the old rig was filled with speakers and developers in different pubs and places. So it was quite interesting. Yeah, so that's our favorite tweet from yesterday. So somebody actually seen beavers tonight. Um, right. So again, thank you to our sponsors for making it possible to run this event. I'll give you a brief introduction about the changes today and what are you going to expect. So okay, we have a schedule. There are a couple of changes. So Mikhail is not coming today. So instead, Dui Hai will tell another presentation about Cassandra graph databases, which is fairly connected, but a bit different. And the second change from the original schedule, which you have in printout. So Martin was talking yesterday instead of Camille, and Camille will talk today. So this is all. So no more changes. Maybe some unexpected ones will appear as we go. Yep. So what's next? Mobile apps. So that's an Android conference, and yesterday's we had plenty of problems with mobile apps. So all people were ashamed. I mean, who were responsible for mobile apps, and overnight they've released a new version. So you could download an update of an Android app, and now it should work properly. Which means that we really encourage you to leave all feedback for yesterday's sessions. You could do it for yesterday, today as well. So vote for all the sessions for yesterday, and at the end of the event, we'll see who will win. So we didn't fix iOS app completely. It's better, but it's not 100% because in order to get an updated app in iOS, you need to wait for 3-4 days. So workshops day tomorrow. So there's a separate ticket for workshops. So there's a conference ticket and workshop ticket. So workshops aren't going to be in Radisson Blu Hotel. So this is how you figure out if it's workshop location or not. We're starting at 9. There will be 4 instruction-led all day long courses. Java 9, Oracle related, DevOps, and Amazon Web Services. So you had to pre-register on one of the courses. If you didn't do so, you could do it on the venue as well. So there are 4 conference rooms in Radisson Blu waiting for us. There will be lunch and coffee breaks as well. Another update for tomorrow. So Alexei went to San Francisco to Google I/O, and we will have a live translation of Google I/O keynotes tomorrow in the cinema at 7:30. So it's a free event for a couple of hours. You're invited to come as well. What else? So we'll have a conference closing at 6:45 today in room 3 here. Some of the sponsors will be raffling their prizes, so that's one of the motivation to go. Another would be we would see who's the best speaker and maybe have some other updates. So that's it from the official part. We've actually prepared a quick overview of how yesterday was going. Just a second. Okay. Do we see it? No. Yeah, that was a bad idea. So as you know, Riga Dev Day gathers a lot of professionals from Baltic states and beyond who are interested in topics like Java, Oracle development, Android and such. So this year it's a little bit different, so we have expanded to a wider auditory.
We had for the first time opening in escape room, and we had a great performance by people from US, and we have great speakers.
To be honest, this is my first keynote in my life, so I was really honored to be here and open the conference. And I thought that even though the conference is technical, I should make the opening speech less technical and more about abstract things. So my talk was about where we were 20 years ago as programmers, as an industry, and where we are right now and what's changed over the last 17 years, and then what's going to happen in the next 17 years.
We're a very young industry. Things change rapidly. Every month, every day, there is something new. And if you, as a developer, are not keeping up, you will lose value in the market, let's say.
We call it a conference, but really I think it's training, because you can come and see lots of short sessions to find out something new that you didn't know about, maybe explore new technology without having to spend a lot of time. And of course, some of the people presenting have spent weeks, months, maybe even years working with this technology, and they're able to condense everything they've learned from all that time down to 45 minutes, so you can get all their experience, all their wisdom in a very short time. So I think that's a great thing to say.
So I was talking about the Internet of Things and how you can use it with Android. So being an Android developer, how you can start building Internet of Things using the technology you already know, but now moving into devices. And yeah, the reaction was pretty good. I had some really good questions. I had some people come in and ask me very interesting things about things you can do and things you can't do, what are the limitations and everything. So it was very good. I was very happy with it.
Yeah, so it was a presentation about 2 mobile applications we developed for our customers. At the end, it was more or less like lessons which we learn about these 2 different projects, and how to succeed if you as a developer or a solution designer or IT manager making enterprise mobile app.
I am from Oracle User Group Norway, and I'm also having a big conference every year. So I'm here just to gain experience, to see how 3 user groups can collaborate together. I think that was it's a new experience for me, because we don't do that. We only use Oracle partners.
For the first time, we've had a user group summit hosted in Riga, where other conference and meetup organizers have met together and discussed how to improve their operations, so to say. IT conference for developers are a mixture of inspiration, a show, and an education. So you have to have all 3 aspects to run a successful conference, because nobody really likes to listen for a boring content if it's not fascinating, if a speaker isn't a professional performer. And at the same time, you would need the content to be technical enough and applicable at your daily work. So today we have a little bit different topics. As a Java person, I find that today is more interesting, because there are quite a few very hardcore and in-depth talks. For example, a talk by Heinz and a talk by Andre. And also we have more attention to database and cloud infrastructure, which is very popular nowadays, and I recommend going on these sessions as well. Okay, so that was day 1. Yeah, right. So the next topic on our agenda is another of our great sponsors, and we will start introducing them in a minute. Sound from computer.
So this conference couldn't have taken place without our general sponsor, and please make a warm welcome to Oracle general sponsor.
Okay, thank you and hello. Hello, laba diena, labrit, tere, dobry den. This is a Baltic conference, I can say, and big thank you to the Latvian user group. And this is really a great thing that in Latvia we have this user group. Unfortunately, in Lithuania, we don't have such a fortune of having an Oracle user group. So that is an invitation from my side. If anyone would like to take a lead and to be the initiator of that, so please come over to our booth here on the 4th floor. So we will make sure to support you at the beginning, but then all the great things happen in the community already, which we see as an example of this conference. So, my name is Andrius Kunčikas. I'm the manager of Oracle representative offices here in Baltics, Lithuania, Latvia, and Estonia. And I have an honor and the pleasure to kick off this day 2 of Riga Dev Days, this wonderful event. And I have 2 good news for you. So the first good news is that this is going to be the shortest and the fastest presentation you will see today. So that's that's one thing. And second thing is that you will have 3 takeaways from my presentation. So let's start with the introduction of my colleagues. By introducing my colleagues, I want to say that here at this event, at Oracle booth, you can meet them, but it's not the only place where you can meet them. So any day after this event, I'm encouraging you to reach out to my colleagues and to discuss what's important for you. And looking at the pictures, so you can most probably distinguish who is the technical guy, who is the sales guy, and who is managing partners, you know. So yeah, these are the colleagues. So meet them at our Oracle booth. And the responsibility of each Oracle representative is to make sure that each of you would get everything that is the best from Oracle side, and in the way that is most convenient, either for you personally or for your companies. So, and there are traditionally like 2 ways. So the traditional IT way, which we call on-premise, so it's still existing. And obviously all the industry is shifting towards the cloud. So Oracle is as well a cloud provider, and we can offer you those services. So that's the first takeaway. Second topic that I want to introduce is that Oracle is a global cloud services provider, and we have services in each layer: infrastructure, platform, and software as a service. And for this audience, for the developers, so I think most of the offerings which you will find suitable for you and important for you are in the platform area or in the infrastructure area. So I encourage you to have a look at those. And those cloud services are being provided from data centers in the multiple locations globally. So we have more than 19 data centers currently, and in Europe we have data centers as well. So in first of all, starting with the Netherlands, Amsterdam, then Great Britain, and with the recent Brexit agenda, so the expansion in the European Union is going towards the Germany. So last week Oracle opened a brand new data center in Germany, which is best in class and offering the high performance cloud services, and in the most efficient way and a secure way. What is unique that Oracle is offering bare metal cloud services for the customers across European Union, And this can be a perfect platform for your enterprise level type of applications. So which means that this cloud service is delivering the highest performance that is possible from the cloud services. And what is the most important, this infrastructure is being delivered according to the all highest standards of the security. And security these days is becoming more and more important. And security has many aspects, as you know, and we shouldn't look only at the IT-related issues. We shouldn't underestimate as well the human factor of the security. And with that, I want to emphasize, and that would be takeaway number 2, that European Union released the General Data Protection Regulation, I can call it a law, which each company who is dealing with personal data has to comply with. This law will be in force starting with 2018 May, so we have a year to comply with that and to prepare for that. So for each of you who are developing applications, you should have a look and take care of the security, because in case of any data loss, data theft, any breach, so there are significant liabilities and sanctions that can be imposed to the companies of the significant size. So with that, the takeaway number 3 from my side, that Oracle can be your partner, or is already a partner for many companies or individual developers who can provide performing and highly secure infrastructure for your applications. And as I said, it's possible in both ways, in on-premise and in cloud fashion. So with that, I will conclude my fastest and shortest presentation, and with the 3 takeaways, and encouraging you to visit our Oracle booth here on the 4th floor and to discuss what is important for you, and wishing a good and productive day for you. Thank you.
Thank you so much. And the next on our list is a special keynote speaker who came all the way from sunny Brazil. So I would like to introduce Edson Yanaga, who is a Red Hat developer advocate. So give you an applause. Thank you. So,
Hello, sound check. Perfect. So let me put this aside. And Labrit. Okay. In fact, I rehearsed 2 words. It was supposed to be good morning, everybody, but I forgot the second. So forgive me. At least I think I did the hello part right. And as Dimitri said, I'm very happy to be here at Riga Dev Days, as I think I'm the only Brazilian Japanese here. There might be any other Brazilians here? No? So the only Brazilian, at least for now. So I traveled a long way to be here, and I'm very proud to be here with you today discussing DevOps. And I always like to think that we are always discussing DevOps, and people say that DevOps is a culture, is our processes or our tools. I like to think that instead of just telling people how to do it or what they should be doing to automate the things and how to deploy software into production. They should be learning why we should be doing the same things. That's why I chose this topic for this keynote. I hope you can enjoy what I'm going to share you today. Currently, I'm a director of developer experience at Red Hat. My Twitter handle is @Yanaga, and I talk a lot about DevOps, microservices, Java, and domain-driven design. Just in case you want to follow me, I share a lot of the content about it. And I'm also a Java champion and a Microsoft MVP, which I know it's kind of a weird combination, but we are living in different times. The world has changed in the past few years a lot. And that's something that pretty much represents. And I'm very proud to be as Java champion and an MVP. I was to also work for Red Hat, the largest open source company in the world, which means in the end that open source has won. Open source Java has won. Open source Java software development has won. And even the largest proprietary software company in the world now is adopting open source. So it means that in the end, we, from the open source community, we did something right. And I've been advocating for open source development and open source software for many years, even before I joined Red Hat. That's why I'm so happy to live in this wonderful new world where open source has become the default method of developing software. And I always like to start my sessions, my talks, with this sentence from Forbes, which now every company is a software company. You don't work for a bank, you work for a software company. You don't work for an industry, you work for a software company, because we live in this thing that we are calling now digital economy. And I'd like to tell you something. I've always read and thought about economics or economy, about something that was related to money. But after reading some economics book, particularly behavioral economics, I became very interested in the subject. And after that, I started to study also behavioral psychology. Even though I'm a deep technical person, I like it to learn about how people interact with each other. And economics is all about that. Economics, it studies how people behave in a certain system, and which constraints on the systems can you impose on people to change a system from one state to the other. So instead of studying money, we're trying to study how people behave, how people interact with each other. So this new digital economy means how are we as people interacting with each other through software. And some of the great examples that we have from this new digital economy is that the largest car transportation company in the world owns no cars, which is Uber. The largest lodging company in the world owns no real estate, which is Airbnb. The largest online retailer in the world owns no stock, which is Alibaba. And the largest content network in the world produces no content, which is Facebook. All of these companies, they have something in common, that they are enabled through software. So software is changing the world. So from this new digital economy, I started to think about what is the purpose, why we as software developers, why are we here as people? What makes us so special, so we consider ourselves so special? So I also think that we really are the most important people in the world right now, because I have an absolutely confidence that no big evolution or revolution is going to happen in the next 1,000 years without a software developer behind it. So if you're going to find a cure for cancer, or cure for hunger, or maybe cure for world peace, if you're going to try to find world peace, it's going to happen because a software developer is behind it, because software is enabling different ways to change the world that we live. That's why I like so much this quote from Mark Twain. It's one of my favorite ones, which states that the two most important days in your life are the day you are born and the day you find out why. We are all here today, that's because we were born, but maybe not all of us have found out why are we here. And I have a personal testimony to tell you today. Some years ago, I was very disappointed with my profession as a software developer. I found out that maybe I could have chosen something different to do in my life. Maybe I could be making more money, doing something different. And I don't know, like 6-7 years ago, I was even trying to do something else in my life. I should try another profession, try to do anything else. But fortunately, or unfortunately, I've also learned that the only thing that I knew how to do in my life was software. So it better, I could, instead of trying to do a different thing, I could try to see what I do in my job in a different way. And it was very important to me to find some kind of purpose, because I think that I was developing software in a meaningless way. And now then I realized that our profession can be wonderful, but also can be miserable. And I also had one of the greatest lessons that I've learned in my life when trying to deploy software in production. I always try to do the best code that I ever could. I'm a very fan of clean code techniques, and I consider myself also a software craftsman, which is somebody who cares about what he does and how he does it. So I realized that I could fulfill all of the requirements. I could take the specifications. I could deliver great software, great crafted software. But also I did a major system for healthcare and insurance companies in Brazil. But the day I deployed that into production, that was one of the worst days in my life, because the software, I fulfilled all of the requirements. But then I started receiving calls that people were complaining because it was working, but I just received a lot of complaints. Then I said, it's not right. The software is working. And then I decided to go to the clinics, to the doctors, to the nurse, to check what was happening. And that was the worst experience in my life, because I never felt so miserable. Because I saw that even though the software was working, I was making that people's lives much worse than was before. And I made a promise that day that I would come back 30 days later, and I would change their lives for the better. And that's one of the greatest things that we have in our jobs, when we are able to take something that we coded, to release that in production, and see people using that, and we can check that we are improves their lives for the better. So sometimes all we need is to be held accountable for what we're doing, and to see that we can make the difference in the world that we live. So if we all are as such important as we believe we are, if everything in this world is going to happen because a software developer is behind it, then I think we have to make a decision, we have to make a choice, and to find a purpose. I've decided from that day on that I would want to make people's life better and not miserable. So I think that if you're all today trying to uncover new ways to develop software with new techniques and tools and different ways, we're all trying to improve ourselves and trying to deliver better software to make people's lives improve for the better. And I don't know how many of you have watched this TED Talk or checked the Simon Sinek's website, startwithwhy.com. Anybody? Okay, it's a very interesting talk. It's like 7 or 8 minutes long. I think you should all check. But if I could just take the key takeaway from his talk, it means that for everything in life we have 3 big circles: the circle of why, the circle of how, and what. And if we really want to change the way that we think about something, or if we want to try to convince people to change something in their lives, we should always start with the inner circle, which is the why. Because if you know why are you doing something, then the how you should be doing that, or what should you be doing to achieve the why, and then it becomes just automatic. So the question that I have for all of us is, why are we doing what we're doing as software? And if we think that DevOps and microservices are an interesting thing to be learning about, why should we be adopting DevOps and microservices or any other technique instead of just consuming technologies and tools because something is new or something is telling us that it is good? We should learn why should we be doing what we're doing. Which leads us to our question: we as software developers, or we as operating persons? In fact, I would like to ask, who is a software developer here? Who works on IT operations? Okay, 30% share. And I'd like to, this question especially target to software developers, because we usually have a different mindset about when is my job done. So is my job done when I simply get an issue on Jira, code a thing, maybe I test it on my machine and it works, and commit that to source code. Maybe my job is done, my continuous integration server is finished. Maybe my job is done when software, when I generate a release of my source code. Or is that the right thing? What is the definition of done that we have for software? And this kind of misconceptions about when my job is done generate some interesting memes on the internet. This is one of my favorites, because we always have that bad sensation. We as software developers, we have some shivers when the release day comes for us. So, you know, the release day is that big day. Everybody gets to be prepared. Come on, we're going to release software this night. So tomorrow morning, everybody, 6 a.m. needs to be ready, because it's going to be chaos. There are going to be bugs. People will be calling our names and everything else. So thinking about our lives, that stressful moment, maybe we should be needing to deal with this event in such a way. Maybe it should be a non-event. Maybe it should be a normal thing to be releasing software in production. But I understand why people try to postpone releases, why people try to avoid releases, because we as humans, we try to avoid things that causes our pains. Well, unless you're a sadomasochist, then you try to get that earlier. But yeah, if releasing software into production is something that induces you pain, you try to avoid it. So if you're releasing software every week and it gives you pain every single week, then what do? You just postpone that, right? Because then you only want to software like twice a month. Then it gives you pain anyway. So you only want to suffer like once a month or once a year. That's why we're always delaying our software releases. We don't want to feel this pain. And to try to solve that, many people advocate that DevOps is the way to relieve you from this pain of releasing software into production. So just to introduce you for the term, DevOps usually originated, we have two different teams working in trying to release software or to maintain software in production. We traditionally, in bimodal IT companies, you have developers and IT operations, and they are separate teams. So trying to contract these names, we coined the new term DevOps. And again, I don't know how many of you have read the book The Goal, but the key takeaway of the book is that you tell me how you measure people, and I'll tell you how they behave. So that's why we think that Dev and Ops are separate teams, and we have like a wall splitting people. And I can tell you that in traditional bimodal IT corporations, the dev guys hate the operation guys, and the ops guys hate the dev guys. Why? The dev guys are usually the guys that want to explore new things. They want the new framework. They want the new version of application server. They want the new version of the database. They want that new shiny thing to be deployed into production, because developers, they are held accountable for the new features that they are releasing into code. Developers are held accountable for changes. Developers need to change things because they need to deliver new things into production. And the operation guys, they're held accountable for stability. They're the ones that are supposed to not let things break into production. So the less downtime you have into production, the better, at least the better is considered the ops team. And how can you be friends of somebody that is constantly screwing up your life when you're the person that every time you release the software into production, you just make his life horrible? You can't be friend of somebody like this, right? So that's why developer and operations always have this constant battle. We are fighting against each other because one side has to deliver new features in production, has to change things, and the other side is supposed to not break things into production. And the best way for you to have stability into production environment is to not change things at all. Yeah. So maybe we need to change some things. Maybe we need to change. We developers, we need to change the way that we think about our job, or when our job is done, or how should we be releasing code into production. Another great meme from the internet is the Disaster Girl, which basically proposes the paradox, which is the famous sentence that every developer has ever said in their life, which is, but it works on my machine, right? And I always used to do that, but on that same system, healthcare insurance system that I released in production. One of the releases that we did later, it was a major pain. We had a bug that was seriously provoking some problems into production. Then we were trying to find a fix for that, but the phone just kept ringing and ringing and ringing, and I was asking people to stop calling our office because we had to fix that bug. But then the president of the largest health insurance company, which is our customer, decided to call me directly on my mobile phone, and I was telling you know that we're having a lot of bugs into production. You're supposed to fix that, and I said I'm trying, but I have to tell you, it works on my machine. Then I had one of the biggest insights I've ever had, because he was really pissed off. He was calling me names, but he said that to me. People in Brazil, they call me Yanaga, and he told me, Yanaga, I'm not telling you, I'm not paying you to make the software work on your machine. I'm paying you to make the software work in my machines. And then I just had this moment of silence, and it was there. Hello, hello, are you there? Yes, I'm here. And you are right. It's not supposed to work on my machine. Of course it does now, but it's supposed to work on your machine or your production environment, because in my notebook, it doesn't matter. The really thing that matters is the code that is running into production. And that's the day that it changed my mind about how I see how we should be releasing software into production. And in fact, many developers avoid trying to release software into productions because they don't want to be held accountable for the consequences of their acts. And we know that every time somebody is not held accountable for the things that they do, bad things happen. So I decided that I wanted this responsibility. I wanted to be held accountable for what I do, because I want to be blamed guilty when something goes wrong into production, but I always want to be considered responsible for the good things that are released into production. And we, again, as developers, it's kind of very frustrating to be spending a lot of time developing some piece of code that you think that it's beautiful because you've done it properly, you've done it the best way that you could at the moment. You spent like 1 week or 1 month developing this special feature, then you just commit that to the source code repository, and it takes like 6 months for you to release that into production. When it goes into production, you don't even remember what you did 6 months ago. You don't even know if anybody is using that feature, or if that feature is fulfilling its purpose, if it's improving users' lives for the better. So when we take this from developers, we just feel miserable, because what is the purpose of what I'm doing? So we, as developers, we also need to see the consequences of the code that we're producing. If we can establish a direct relationship between what we code and the consequence of that, the problems are bad, but the good things that we deliver into production also, it motivates us to do even better. So we lost that feeling sometime. I don't know how many of you remember when we were learning how to code, when we were able to code the very small things, even if it was a hello world. Oh my God, I did something that works. And for many enterprise companies, you can't have this feeling anymore, because you don't even know what are you doing, or when it's going to be deployed into production, or if it makes any difference for anybody's life. So maybe we need to get this back in our lives. And when we're talking about DevOps, this sensation that our life doesn't have meaning because what we do, we can't see that working and improving people's lives. Technically, the term that leads to the amount of time from idea to production, to making people's lives improve for the better into production, we call that lead time, and that's one of the ways that you can measure. So lead time is the amount of time from idea to production. And from DevOps, one of the key takeaways, there are 3 big measures that we try to improve when talking about DevOps. One of that is the lead time. We should shorten our lead time, because the better the better the feedback loop, the smaller the lead time, the better is the quality of the things that we deliver in production. And as I said, the feedback loop is one of the most important concepts from human life, and also, of course, we apply that to software development process too. Remember, the feedback loop is, that's why we as humans, we learned how to talk, because in the beginning we didn't know how to talk. Then we tried to repeat some words that our parents or grandparents were speaking, and we needed their feedback to know if we were saying the right sounds for later to be composing some words and everything else. When we were coding, remember when all we had was like a notepad or a blue screen with yellow fonts to be coded and everything else? We need to compile to know if the syntax was right. These days we have like IDEs that can syntax highlight, and some of them can even do continuous testing of your software to check if you're doing the right thing at the moment. So we improved the feedback, so the software that we're developing is better too. Then if you think about all of the major improvements that we have in the software development process in the past 40 years, they are all related to the feedback loop, because then we introduced something continuous integration. Because if you remember that, I don't know how many of you were in the software field at that time, but like 20 years ago, integration was one of the biggest issues that we have in the software development process. Because the only day that we did software integration was in the release day. And I have to tell you a story. One of the largest public banks in Brazil, there are not many, so if you Google that, you would be able to find what was that, but I'm not authorized to say the name. And what happened is that developers used to code their things, and they were using CVS at the time, and they used to commit. And if you're using Git now, you're cool. But if you remember, CVS they didn't have atomic commits, so you could commit something by half, have a conflict, have to solve, and then commit the rest of the changes that you were supposed to push to the repository. So at this big bank, people were just coding and committing and releasing things to the repository, and the only day that somebody integrated software code was in deployment day. But on that, usually this process was done in Friday, 6 p.m., which is the time in Brazil that people leave to their houses. Everybody but the ops guys. So developers were very happy. Well, 6 p.m. gone. This weekend is release day, but not my problem. Then the ops guy, they decide, well, now we need to deploy that thing into production. Then we're trying, that's the day where ops guys check out the source code from the repository. And at that time, they were using Ant. So they had to generate like an Ant builder of the code. But since nobody integrated the code before, many different teams trying to work together, they tried to compile the code. It didn't work. That's the interesting part, how you motivate people. The ops guy learned how to program in Java. How much? Just enough to be able to make the code compile. So you see, you had a lot of different code from different teams and people, and you check out the source code on the deployment day, you try to compile that, and it just doesn't compile. You have a lot of compile errors. So they learned how to comment code. So what they did that, every night, this file is not compiling, which lines? We just comment that out, and the other file, now these other ones not compile. So they learned how to keep commenting the source code files until the project was able to generate a war file, and then a near file. Then they spent the whole weekend doing this thing and deploying the thing, so that Monday, 8 a.m., everybody would have the new release of software. And for some unexplainable magic, usually it didn't work, right? So that was how integration used to be done 20 years ago. I don't know how many of you do that today. Maybe not many. Okay? So then we decided that, we needed to integrate more often to prevent this kind of mistakes. So we created something like continuous integration servers, that there are continuous integration every night with nightly boots, or every hour, or maybe if you have a very fast build cycle on each commit that any developer produces on your source code repository, you're releasing a new version or potential releasable new version in your continuous integration server. So if anybody breaks anything, at least in your source code or in your test, you will be able to, in a couple of minutes or at most like in a couple of hours, be aware that something was broken. Okay? And again, we improved the feedback loop because it doesn't take anymore 2 months to know that I've broke something from from the other part of the code. Now I can know in just a couple of minutes or a couple of hours at most with a continuous integration server if I did something that is wrong. So it's much easier for me to spot because the thing that I just did on that commit is breaking others, so I can find the bug very easily. And before joining my current job, I used to be an independent consultant for more than 10 years, and I used to try to help people in the past 5 or 6 years to try to release software faster and more safely into production. I've been working with DevOps, but I only learned that there was a word for that, DevOps, some years later. And the number one question that I always make when I visit somebody, some company, some teams, was what prevents you from delivering faster? So maybe you want to deliver software faster, not every year, not every 6 months, but reduce that lead time. So what prevents you from delivering faster? Any suggestions? What prevents you from delivering faster? Cycle time, which, well, we'll explore later. Cycle time, lead time, and batch size, they're all interrelated. They're all measures that influence the same, have the same consequences. It's even more simple than that. Coffee. Not enough coffee. Business. Yeah, you don't release fast because you have business requirements that change a lot of business requirements to cause. I won't explore, but usually I take some time discussing with the teams, as I used to, at least as a consultant. But the number one problem that all of the teams that I visited had in 100% of the times was bugs. We don't release software faster into production because when we release software, we have bugs. So we need more time to test. So if you're releasing software every week, we can't release software every week. We need more time to test. So we need 2 weeks. But people don't realize that when you have more time to test, you also have more time to code. So there's never enough time to test. Because if you say that you're only releasing software every 2 weeks, people are going to require you to code more features in the 2 weeks time frame. So you're never going to be able to test enough. But you're still having bugs into production. And the point that people don't realize that usually we try to think that the more time that we have to release a new version of software, the more stable it will be. The lesser the bugs we'll have. But in fact, it's the opposite. If you think about the economics of software deployments, the question that I'll try to establish a very simple correlation or very simplistic correlation. Which causes bugs into production? Say, when you release a new version of software, which causes bugs into production? Changes causes bugs into production. And changes usually can be caused, the source of changes can be targeted into 3 different points, which is usually what you change from one release to the other, or what changed from one release to the other. Your code changed, your environment changed, or your data changed. So let's try to oversimplify again. So I can tell you that we, as software developers, the things that causes bugs into productions are changes in our code. So if you think about in a simple correlation, the more changes that you have in a single release, the more bugs that you have into production. So what are we doing? We're increasing the amount of change that's released in software production, and we're expecting to have fewer bugs. Instead, why don't we think the opposite way? The fewer the things that we change into the code when we release software, the lesser the bugs that we have into production. That's the DevOps thinking. If we are able to reduce the amount of change that we do in each one of our versions, we will have fewer bugs into production. And this measure, technically, we call that batch size. Batch size is the amount of changes that you have into each one of your releases. And if you are able to reduce the batch size in your process until, like, if you're doing like 1,000 lines, if you're able to constantly reduce the amount of the lines that you deliver into each one of your releases until maybe the idea of amount of one commit, one small commit of code into one of your releases. If you just committed 15 lines of code and you release that into production like in a matter of minutes or 1 hour, 2 hours, if you committed that and 30 minutes later, that is causing bugs into production, where is the source of the problems? Isn't that very likely that the source of the problems, the root of the problems, is the single 15-line commit that you did that. In fact, teams that have very mature software deployment pipelines, instead of having rollback strategies for rolling, getting back the previous version, if they have very small commits to be deployed into production, it's much easier for them to spot the bug or the problem on the commit that they just did, release a new version, and deploy that into production instead of having rollback strategies. So, as I said, and the batch size, cycle time, and lead time, they are all interrelated, because the smaller the batch size you have, if you have very small changes in each one of your releases, small batch size means that you have a smaller lead time too, from idea to production. It also means that you have a smaller cycle time, because you're releasing more often, so the time of your cycle of releasing software also is reduced. So they are all interrelated measures. So if you think that if you're improving your batch size, you're also improving your lead time and your cycle time, which are the technical measures that we use when we're talking about DevOps pipelines and software development process. The second largest causes of excuses that people have for not releasing software faster are people. We don't release software faster because the ops guys, they don't allow us to do so. We don't release software faster because the DBA is not my friend. When I ask them, or him or her, to change a column, it takes 2 weeks. I have to open a ticket. Yeah, they will resolve the tickets at their will, and they will not notify me, so I don't even remember why I asked them to change the column. So people is the source and the solution to most of the problems. So maybe the answer is that, okay, you don't like the DBAs, but when was the last time that you had lunch together? Maybe it's easier for you to ask people to change something if you know the person, if you at least know the name, to blame later. Well, maybe. But if you know the people, it's easier if you have a closer contact with the people that you work with. Maybe you get the process easier. And that's why I've been so amazed by behavioral psychology and behavioral economics. That's how you can interact with people, how you can learn the motivations that people have to be doing what they do. You see, you change the restrictions that people have on their system, you change how they behave. Many people say that DevOps is a culture, and the best definition of culture that I have is that culture is what you do. So if you're able to change what people do, you're changing the culture of the entire company. And again, processes are just the repeated ways of you doing something. So if you're changing what people do, you can change everything, but even better. You know, we all know, it's hard to change people's minds. It's hard to change what others people do. But software is a system. We are all people interacting with people. And if I have to tell you that if we can't change others, how do we change a system which has a culture? Everybody's doing what they're doing and nobody has the motivation for doing so. But if you want to change anything, if you want to improve anything, maybe you can start by changing yourself. So any DevOps change, any DevOps movement, any DevOps culture change, it never starts with the upper layers telling you to, oh, you have to do DevOps. Let's create a DevOps department. Let's hire some DevOps people to try to do the things. No, the changes starts with yourself, and then maybe you can change the others, and later you can change the process that you have in your company. Because all of the top-down approaches that I've seen about trying to impose DevOps to people never work, because people do what they think is better for them, and people rarely see the outcome of the entire output of the company. So if you can make people responsible for what they're doing from the whole pipeline and not just single points, then maybe you can improve the way that you're releasing software into production. And I say that with all of these problems, bugs and people and everything else, there's only one way to solve these problems, and so I might sound a little silly here. I'll say that the only way for you to solve these problems is competence. But see, it's obvious. But then I learned it 3 years ago. I visited a federal university in Brazil in Uberlândia, which is the land of Uber. Yeah, okay, I'm kidding. But This professor, he told me one of the greatest definitions I have of the word competence. He told me that competence comes from the Latin word which is competere, and competere originally it didn't mean the notion that we have from, because when we think about competence we think about competition, but competence is not about competition. The original meaning of the word competere means improving ourselves together. Another meaning that we have in original Latin for competere is we are competing, but we're not competing against other people. We are competing against ourselves. So if you are a person that is competing against yourself, and by the end of the day you win, you have to win, right? You're a better person than you were before. Tomorrow you're a better person than you are today, and today you are a better person than you were yesterday. That is the definition of competence. So competence has everything to do about self-improvement and is not related to proficiency, because I thought that competence and proficiency, they were similar things, but I realized that proficiency is the ability for you to do something well, but for you to be able to become proficient, you have to first be competent, because you have to be improving yourself all the time to reach this proficiency. So maybe we can one day reach software deployment proficiency, and for that the answer is we need to be competent. We need to be improving ourselves. We need to change. The only person that we can change in any system ourselves. You see, in economics we say that if we change one of the restrictions of the system, you can change the entire state of the system. So if you change the restrictions upon yourself on how you do things, maybe you can change the entire system and how other people behave too. Because if you are changing just a little thing, if you automate just a little thing, if you just talk to people and try to work closer to people, to try to release software faster and better, then it can be a reaction chain. You will be able to change a lot of other things. And many people have come to me in the past months and years saying that I thought it was silly that I wasn't able to change anything in my company and in my process, but after doing that for many weeks and maybe months, they were able to achieve something, to change something. And you see, when people see the changes and start to see the results, oh, we're releasing software faster, we have fewer bugs. Now I know the guy that deploys my code into production. Now he's able to call me by my name. I'm able to call him by his name or his or her name to know how things is going on. Yeah. Maybe when you change the restrictions on how you act on your process, you can change the entire output for the better. But just, I have just a few minutes, so just to give you also a technology landscape, because new technologies suggest you newer ways for you to do the things that you did together, and something that definitely changed the landscape on how we deploy software into production the past few years are containers, which are not a new technology, but something happened in the past few years that made us adopt containers as software deployment artifacts units for our code. So talking about containers, of course, I have to make this analogy with real-world containers. And if you think about real-world containers, some great statistics of containers is that in 2010, containers were responsible for about 60% of the worldwide trades in the economy. So the other 40% were transported by bulk cargo ships and some small amount by planes. So everything that is not transported through planes or bulk cargo, like soy or oil or these kind of things, is transported by containers. And also, but you think about only 13% of the ships in the world are container cargo ships. So a very small amount of ships in the world are responsible for all of 60% of the worldwide seaborne trade that we have. So containers, they have something special. But what is about containers? If you think, I don't know how many of you remember the movie Titanic, and if you see how they were packaging the things to get into the ship, if you know, the people were tying the bicycles together, we were carrying the sacks together to put that on the ship. That's how the shipping used to be done before containers. But container technology in the ships also is kind of recent, because everything only happened after the Second World War. Then in the beginning, we had different companies providing different types of containers, but then everybody realized that, well, it's not going to be easy if we need this container size, needs this ship, and this other container size needs the other ship. And imagine the people from the port. I need different equipment to be moving this container size, and other kind of equipment to be moving this container size. You see, we used to be specialists in carrying goods from one place to the other, from one place to the ship, and from the ship to the port. When people created containers, the guy from the port, the only thing that he needed to learn was how to use the crank to get a container from the ship to the port and back and forth. That's the only thing that they knew. We don't need bicycle shipping experts. We don't need banana shipping experts or anything else. In fact, bananas, most of the bananas in the world are produced in Africa. In Brazil, we produce that too. And we export these bananas too. But bananas, they have a very specific temperature in which they must be transported, or else they will spoil. But the guy from the port, he doesn't need to know how do I have to take care of bananas, because the containers know which is the temperature that bananas must be held during transportation. So they have an internal refrigerator that keeps the temperature on that constant temperature from packaging to deploying that to the customer. So everything that the guy from the ship needs to know is, oh, this is a refrigerated container. It must be plugged in a power outlet. So it became very easy for people to transport goods through ships with the advent of container. But we're talking about containers in software. What is so great about containers in software that changed the landscape that we have today? First, just as the physical containers that we have in the shipping world, containers in the software allow us to have resource consolidation. How is that? If you think about traditional virtualization, which was the previous generation of resource consolidation that we have, we thought about, well, we're not using 100% of capacity of our servers that we have in our data center. Then maybe if we virtualize, we can improve the resource utilization so we can have more things running on the same hardware. Software virtualization allows us, and traditionally, we have a physical server, we have a host OS, we have a hypervisor, and each one of our virtual machines had a guest OS, the binaries and libraries, which were the dependencies of your application, and the packaging of your application. Containers changed this landscape when they allowed us to have just a single server. It doesn't matter now if that's virtualized or bare metal. You have a server, you have just a single host OS with your shared service, like networking service, like file system service, and this kind of things. And each container only packages the dependencies of your application and your application. So it becomes smaller because you have fewer resource consumption, you have fewer memory consumption, fewer CPU consumption, because you don't have a entire operating systems running into each one of your VMs. You don't have an entire copy of your kernel running into each one of your VMs. If you're using like Windows installation, you don't have gigabytes and gigabytes of disk being consumed by the exactly same copies of the things that you have. And what motivated that? Because somebody realized that it's a good practice when you have a data center to manage. Even if you have a lot of different VMs, it's a good practice for you to have the same operating system version in all of your VMs, to have the same version of patches in all of your VMs. If you're using an Apache web server, you want the exactly same version of your Apache web server in all of your VMs. Then people realize that everything is the same. Why can't we share these resources between many different applications and just deploy what changes from one VM to the other? That's where the container landscape came from. When we had enough technology to isolate each one of our applications from interfering with each other, with the container technology has popularized it, right? So now we can share the file system, we can share the applications, we can share the kernel, the process manager, the memory manager, the networking stack, we can share all of that so that we can have containers which only packages your application and the dependencies of your application in a small single package. So we have the resource consolidation because we're consuming less CPU, less memory, less disk, and everything else. And because containers are very small, because you don't have to boot an entire operating system, you only boot an application. It's fast to transport from one place to the other, and it's also fast to start a container. You don't have to wait for minutes for your container to start up. In many cases, you just wait a couple of seconds and your application is already running, because for the host operating system, your container is just a new process. So that's what changed in containers. Containers allowed you to have resource consolidation. But it wouldn't work if we didn't agree on a common format. And in that sense, Docker had a great job because it defined a standard packaging format for containers. So if we agreed on a standard packaging for containers, then it's easy for me to create a packaging format, create in this default standard packaging format. Then you will be able to, your engine, container engine, knows how to run this format, so we'll be able to use it. So I'll be able to create and share container images from one provider to the other. And that's another point. But it used to be possible before too, if we agreed on the same format. But like BSD, Solaris, and Linux, we all had different packaging technologies. And why Docker won in this packaging format space? Well, maybe we had good reasons for that to behave. And again, it's all about economics, how people do that. Containers also allowed us to have what we call virtual appliances. If you ever tried virtual appliances before, once I had the opportunity to try WebSphere as a virtual appliance, but the problem is that the largest machine that we had to run this virtual appliance was a computer. In that case, it was a desktop with 8 gigabytes of RAM. But then the WebSphere virtual appliance, it required 12 gigabytes of RAM to run as a VM, so it didn't fit. So virtual appliances were hard, and it was at that time, many years ago, it was a 12 gigabyte download, so it took like a week for me to download the appliance. And when I tried to run that, I didn't have enough memory. So virtual appliances used to be big, used to be have large memory consumption, large resource consumption. And that's what is a virtual appliance? Virtual appliance is something that turnkey solution. You just, in this case, download a VM and everything is running for you. In this case, I had a host operating system. It was a Windows VM running WebSphere. We have all of the tools, everything else. That's what we call virtual appliance. But containers, since they're small, since they're fast, they allow you to think about a new way of packaging and delivering your software. Instead of asking people to, you need to install Tomcat application server, you need to install a JBoss EAP application server, WebLogic application server. Oh, now you need to install an Oracle database, or now you need to install these dependencies. You need the right versions of these to be working together, and then you have to deploy your application on top of that. Why don't we can package the whole environment that your application depends upon, and your application inside that in just a single artifact, and just say, you just have to run this command, it will run this container, the container has everything that you want packaged all in once. So container changes the way that we package software because it allows us to package dependencies and application all together in what we call virtual appliance. Containers are now used too because container used to be a hard thing to be using, and you needed to be root to create a container and run a container and use a container. Now we have developer-friendly tools. You don't have to be root to be creating your containers, and in most of the cases, it's safe for you as a developer to create your container and run that into production environment because your container is isolated enough to not break things in other containers. So now we have developer-friendly tools to be using packaging containers. And this economics part that I'm talking about, the container registry, I think is the largest innovation that we had in container space in the past 5 years. Because before, even if we decided, we standardize it and we're using this format for containers, Okay, we agree, we have a different format, but if we don't have an easy way for people to publish and consume containers, we would never have developer container technology. And container registry, now we have public containers registries, just like the one in hub.docker.com, which software developers, as we, third-party software developers, we can package our own virtual appliances and publish it to a common public registry. That's the same thing that happened to mobile applications when Apple designed the App Store. Developers were able to publish and then consume easily just by pointing to a single common place, which was the container registry. And just to finish, containers and now what? Envision what we're capable of. Well, containers allow us to package environments and application. So we as software developers, we can create our own software and publish to other people to consume. But we as software developers, we consume software from other developers too. We consume application servers, we consume IDEs, we consume database servers, we consume build tools, which are software which is provided by other developers. Why can't we consume this kind of things as containers too? So imagine Git and software control systems allow us to easily change our source code from one branch to the other. We have a bug in this specific version. We can change and commit the changes. Imagine if we could do that with the dependencies of our software too. I'm just changing this branch. Now I can change the dependencies, or I'm switching projects. I can switch the project from another, and automatically I have all of the dependencies that I need to build the software. This version was built with Maven. This version, it only works with this version of Maven. If I could switch back and forth very easily, very quickly, if I could bootstrap all of my environment as I needed. So if you think, we're just scratching the surface of container usage in the software development world. So first step is to relearn how to package our applications as containers. And second step, I think, is that we as software developers will start to consume software from other developers and integrate that into my software deployment pipeline. And I can envision the future where we have everything on a browser. We just create we see an issue for me to get resolved. I'll click on that, and the whole environment for me to develop, the IDE, the database, the build tools will be all instantiated as containers for me to consume. I'll just commit that. When I commit that, I'll trigger as containers also a build process. We will generate another container as an artifact to be deployed into production. And when the process is done, all of the containers will be destroyed because they're disposable. And I'll be able to get the next issue, and the process will be repeated because containers will change the landscape that we release software to users, and it will also change the landscape on how we consume software from other developers. And that was just a quick introduction that I wanted to talk about with you today about DevOps and containers. And of course, I published some articles and books also on developers.redhat.com. If you feel welcome to please join, and if you want to follow me at Yanaga, I also would love your feedback. And thank you very much for being here today. Thank you much. Thank you much. And I think now you have a coffee break. Okay, so developers need coffee, so take your amount.
won't tell you that, but you're going to have to figure that out yourself. Just whilst we wait for the 5-minute late to happen. And just also whilst waiting, how many of you were here 2 years ago? So not too many. Okay, so it's mostly new crowd. We're going to start in a few minutes.
Okay, so let's start. And now our guest, Heinz Kabutz, will tell his presentation about turbo change CPU utilization in fork join using the manage blocket.
Thank you very much. Right, so how many of you have written parallel code? Okay, I'm going to ask that again. How many of you have written parallel code? Those who haven't put your hand up, put your hand up. Put your hand up if you haven't put your hand up. Because you have. Everybody has written parallel code. All right? Because most of the time, well, all of the time when you're writing code, it's running in parallel. And up to now, we've been very fortunate because the code that we've been writing has been running in parallel without us really having to do anything for it. We've had pipelining and structure level parallelism, and up to now, we haven't really had to pay that much attention because the hardware has been bailing us out. We've been getting faster and faster chips. But there's only so much that we can get with the hardware. Well, maybe they'll make another big breakthrough, but at some point we need to look at solving the problem with software, actually doing some parallelization ourselves. Now, I want to talk about an aspect of parallelism within Java called the managed blocker. It's related to fork join, to the fork join framework. And I did a CPU graph on my little laptop here. It's an i7 Pentium. It's got 4 cores, so it's 4 real cores, and then 8 hardware threads. Because it's got 8 hardware threads, Java, or the operating system actually says that it's got 8 cores. It doesn't really have 8 cores. It's got 4 cores, but hardware threads. So you can see in this graph that the cores have a fair amount of black at the beginning. Once the process starts going, then we have lots of green. Now, we want to have green. Green is good. Red is bad. There's not a lot of red, just a tiny bit of red, which is great. We don't want too much red. Black is also not that good because it means that we're not fully utilizing our available hardware. And we want to try to calculate some large number, and by having a lot of black at the beginning, it means that we're not fully utilizing. Now, what it did was, this was done with fork join, and I'll show you exactly how I got to this. by introducing the managed blocker, I was able to increase utilization of my available hardware, and it started looking like this. So instead of having the black at the beginning, we now have very little black at the beginning, and it completed 8% faster. So an 8% improvement in performance and utilization of my available hardware. Now, we're going to use the example of Fibonacci, which I'm sure you're all familiar with. It's a very easy mathematical sequence, easy to understand. F of 0 equals 0, f of 1 equals 1, f of n is equal to the previous two numbers added together. Now, the numbers get large very quickly, and this is what they had in Australia when the rabbits started breeding without natural predators. They just, children had more children and so on, and they had very, very large numbers of rabbits. And if you implement this as a simple recursive method like this, you can see that the Java code looks very similar to the maths. And if you're a mathematician, you say, well, we're done now. We've written the method, we can go home. But if you try and run this, you'll notice that the performance is beyond dismal. It is absolutely terrible. The computational time complexity of this algorithm is, in fact, itself a Fibonacci series. So it's basically exponential time complexity. Not exactly, but pretty close to that. Now, interestingly, is this algorithm, almost exactly like that, is found in the JDK Java docs. That's why I don't read comments, because documentation doesn't always contain very useful ideas. But this means that if you were to parallelize this, you'd not be able to get very much improvement in your performance, because complexity is so bad. This is another algorithm. This is an iterative algorithm. I'm going from 0 up to n, and all I need is to remember the previous two numbers. I'm not remembering all the previous ones. I'm not working it out over and over again. And now Fibonacci 1 billion is calculated in 1.7 seconds. But the number overflows around about Fibonacci 70 or 80 or around about there somewhere. So the answer's not correct, but it's fast. So that's great. Not very useful. Now we could use big integer to make sure the numbers are correct, and so we don't overflow. But the add function in big integer is also linear. So you've got a linear function multiplied, the linear algorithm of the loop from 0 up to n, multiplied by the linear cost of the add inside big integer, and you get a quadratic function. Now you can work out fairly large numbers, probably 10,000, maybe 100,000, perhaps even 1 million. But you're not going to get to 1 billion. That is 1 billion times 1 billion. It's just too big. It'll take too long to work out. The next one is something called Dijkstra's sum of squares. Now this is not the best formula. There are even better ones than this, but it's pretty good, and it's quite easy to understand. It's basically, if it's an odd number, there's one calculation of adding squares together, and if it's even, then there's a slightly different with the multiply by 2 and some other magic to get to the correct answer. Now, the complexity of the function is logarithmic. So it's like a binary search through a tree. At every point, you're dividing the space by 2. So this is a very nice little function. In previous versions of Java, Java 7 and before that, the multiply inside big integer was also quadratic, so order n squared. And so again, you wouldn't be able to calculate this within our lifetimes, probably, for example, Fibonacci 1 billion. It's just the numbers get too large. In Java 8, they changed that. I'm not sure why, because I don't know how many people actually wanted to do this. And they changed it to have 3 different multiplications depending on how big the number is. Now, you probably know from your studies or experience that a lower complexity doesn't necessarily mean it's going to be faster, because you also, in reality, have to look at the setup cost of your calculation. And so if the number is quite small, then it doesn't pay, the setup cost doesn't pay to use Tomb Cook or Karatsuba. In that case, they're going to just use the basic order n squared that we've always had in Java. The order n squared is like your school mathematics multiplications in junior school, where they try and make you do all these silly calculations. And if the number is slightly bigger, then they take Karatsuba, which has order n to the power of 1.585. And there's a big difference between 1.585 and 2. It's a very, very big difference. You can plot it on a graph. You'll notice they deviate very quickly. And if the object's even bigger, the number's even bigger, they use a three-way Tomb Cook, which is more expensive to set up, but the complexity is lower. So you start winning after some size has been achieved. Now, the big integer is single-threaded. So that's something which we'll fix a bit later. We'll do some hacking and change it, make our own big integer multiply method. So the first step we need to do to solve this is to implement this using big integer. Unfortunately, we don't have operator overloading in Java, so we have to do this a little bit by ourselves. And here's what we'll do. Oh, by the way, what I'm going to do is I've got a GitHub repository. I was going to say a suppository, but that's not the right word for it. Git status. And every time I do a demo, I'm going to commit it. So if I forget to commit, please remind me, Andre, you're responsible for that. If Andre doesn't remind me, then you must complain to him afterwards, please. So just remind me afterwards to commit it every time I do a demo. So the first bit is we're going to implement this using the Dijkstra sum of squares. And if I run this at the moment, for example, Fibonacci 1000, I did an estimate, and I estimated that with the current algorithm, Fibonacci 1000 would take approximately 10 to the power of 200 years to complete. Now, that's just this estimate because none of the atoms that are currently in the universe will be around at that time. You know what I mean? Things are going to be very different in 10 to the 200 years. And I've only got 35 minutes left. So what we're going to do is we're going to change this algorithm to use the Dijkstra sum of squares. It's going to look like this. We're going to have, instead of doing it like this, we're going to say int half equals n plus 1 divided by 2. If n is an odd number, we're going to say return, we need to also say big integer f naught equals f of half minus 1, and f of 1 will be f of half. Then if n is an odd number, I'm going to say return square of f naught. Now, there is a square function inside big integer, but it's not public, so we can't call that. But we can just multiply it by ourselves, and big integer is smart enough to realize it's a square. Add f1 dot multiply f1, like so. Else, return f naught shift left by 1. And then we're going to say add f1 and multiply with f1. So this is the result should be the same as before, except that this is going to be hopefully correct. Right, and a lot faster, hopefully too. So let's run this and see how this compares, if it actually runs. So it now finishes Fibonacci 1000 in 3 milliseconds as opposed to 10 to the 200 years. So we haven't done some improvements. Let's do the entire test suite, and we'll see how long it takes to run Fibonacci 100 million. Now the 10 million and the 1 million are fairly fast. The 100 million still takes a bit of time. Now, the 100 million, we're going to, at the moment, it's going to be, let's see how long it takes. Let's just run for it. Now, I print out the GC just to make sure that there are no full GCs happening whilst we're running. And once it's done, we'll take that time and we'll make a note of it. It's about a minute or so. All right, so the first run was 46 seconds. That's my first run. So that's not so bad. So this is my demo 1. Is that? So let's quickly commit that. Say demo 1. So 47 seconds for demo 1. Now, if you run this, it is running in parallel, but you won't see it. I mean, all the parallelism that's happening is happening on a single core. Right? So you've got your pipeline with that stuff that's happening. It's like almost coming for free to us. But what you'll notice that it is only running on one core. So if you take top, you'll notice that Java's only running 100%. Now, it was at 200% just now, but that could be your hotspot profiler, and it could be your garbage collector running at the same time. So that's why you might go over 100%. But generally, it's just running on a single core. All right. Now, the next demo that we want to do is to improve this a bit and to parallelize the actual algorithm itself as well. So instead of having F1 and F0 and F1 being calculated sequentially, we take F0 and we put it into a recursive task, and then we execute that, we fork that, and afterwards we join that together again. So the idea is to use multiple threads, possibly, depending on how many hardware threads you've got available inside your system, to compute this in parallel. So, and this is going to use the common fork join pool. Because I'm not explicitly specifying a pool, it's going to just default to the common pool. All right, so let's try that. And so recursive task of big integer, F0 task equals new recursive task. And the code here is moved into the compute function. We then say F0 task.fork, and afterwards we say F0 task.join, like so. So now, before we're running at 46 seconds, I'm now running it on 8 hardware threads, but it's not really 8 cores, it's actually 4 cores. So how fast do you think this will run on 4 cores if it takes 46 seconds on a single core? Pardon? The same? You're a pessimist. Pardon? 2 times faster? Why 2 times faster? Yeah, that's a good comeback. I like that. But did you have any specific reason why you said 2 times faster, or just a guess? Very good. Let me repeat your answer, because otherwise it won't be on the audio. So the estimate is twice as fast because you have all the cost of scheduling, the cost of context switching, the cost of doing this whole parallelism, right? And it's sort of a very conservative estimate. So it turns out that you're about correct, but your explanation is wrong. Okay, so let's run it and have a look. Come again, logarithmic of? That would be nice, but it's not going to be logarithmic of previous number. Okay, so it runs for a while, and it is about twice as slow. So you're correct well done on your pessimism. It's just that your explanation's wrong, okay? And if I run, I'm going to run this again, and this time I'm going to have top. Okay, I'll just do that again because I didn't do that fast enough. Stop, start, and top. You can see that Java's running at like hundreds of percentage of CPU. Okay, and after a while, it goes down to like 200%. And then after another time, it goes down to 100%. All right? So we have parallelized our algorithm, but that's not where the main bottleneck is. Or that is some of the bottleneck, but not the main one. You see, what we've encountered here is a very common problem that you have when you do recursive decomposition or divide and conquer. At some point, exactly, at some point you've got to merge the results back together again, and that's when you really start paying the cost and paying the price. So the way that we can get around that is by hacking the big integer to be parallel as well. So let me just commit that, demo 2. And so what we'll do is we'll go to big integer, and we're going to change multiply Toom Cook and square Toom Cook. We're not going to bother with the multiply Karatsuba and square Karatsuba because those numbers are not that big. Remember that Toom Cook is, once the numbers get very big, it's going to be using that algorithm. Now, I must confess that I do understand sort of how the Karatsuba algorithm works. You sort of split the number into two halves, and you multiply the top and the bottom, and the bottom and the top. But I don't understand how Toom Cook works. I've got no idea, right? So, and I actually don't want to know. All I know is that it splits it into 5 equal chunks, and then it does some magic that I don't know how it works. But in the end, the result comes out correctly. Now, the point is that I can parallelize this without having a clue about how the algorithm really works. And that's why I'm not going to try and understand it, because otherwise that will spoil that magic trick. All right, let's try the third demo. We're going to parallelize big integer. So we go to big integer, we copy. Oh, by the way, this is a very effective way to increase your lines of code. Control C, if you want to get a bonus. And then go to Java Math. Control V. Bingo, I've just written like 2,000 lines or something. Okay, now, how do I actually use this class, this class? I haven't hacked it yet. I will hack it in a moment. How do I use it? Well, let me just go to the top and put in a little note that I am using it, so I can confirm that I'm actually using it. Come on now, where's the top? There's the top. Static using hacked big integer. Okay. Now, when I run it normally, it won't actually show that. It will just run without showing using hacked version. Oh, okay, I made a mistake. I'm supposed to start off, and this is supposed to be /a, right? So normally, you wouldn't have a boot class path inside your VM parameters, right? You just have it like this. So normally you wouldn't see hacked big integer, right? But if you do the following, if you say -x boot class path /p, which means prepend, then you can prepend your class to the JDK JVM class. And so you can use your own Java Math rather than the Java Math which is found in the JVM. Okay, so now when you run it, it's going to print out using hacked big integer. Okay. All right, now let's go to our big integer, and we're looking for multiply Toom Cook. And as I said, I have no clue how it really works. I just know that it does some stuff and ends up with 5 different multipliers. 1, 2, 3, 4, 5. And the rule that I give myself to get this to work as well as possible is to only fork once and then join again before I do my next fork. So I'm not going to fork 5 times and then join 5 times, because that can end up actually constructing too many threads, more threads than we should have in the system. It's really a fork one off, join it, fork another one off. So we're going to do this multiply task. V0 task equals new multiply task with A0 comma B0. Now, this multiply task doesn't exist yet. I'm going to construct it as an inner class of big integer, and it's going to be A comma B. For some reason, there was used those for maths. Let's make some fields A, B. This is going to say extends recursive task of big integer. And then inside the compute function, we're going to say return A.multiply B. Now, I want to emphasize again that I've got no clue how the actual Tomb Cook works. All I'm doing is I'm creating a separate task to do the multiplication. So I'm going to do the same thing for square, except I just need an A, and I'm going to say return A dot square, like that. So square task and multiply task, both are static classes. Okay, let's go back to where we were using it. So I make V0 task, then I say V0 task dot fork, which is going to use a common fork join pool. And then once I've done my second multiply and any other work, I'm going to say V0 equals V0 task dot join. All right. I'm going to do the same thing for V1. I'm going to say multiply task V1 task equals new multiply task of DA1 comma DB1 V1 task dot fork, and at the end I'm going to say V1 task dot join. Okay, so in this case I'm actually doing 2 multipliers for the one fork, but that's okay. It's slightly unbalanced, but it's still going to work well enough, I think. Now, I could also do Karatsuba, but Karatsuba is likely to, it's not going to make a big difference because the numbers are going to be too small. But it would be fairly easy to patch this into Karatsuba as well. Let's do the square Tomb Cook as well. Here we're going to say square task V0 task equals A0 dot, new square task of A0. V0 task dot fork. No, why doesn't it? What's complaining about here? Ah, right. Don't need that. Dot fork. And then after before I do the third square, I'm going to say V0 equals V0 task dot join. And again, square task V1 task equals new square task, this time of DA1. And fork that. And then at the end, we're going to say V1 task dot join again. All right, so hopefully this is going to get us better performance, right? Hopefully we will now be able to do 4 times faster than the original. Right, so we're hoping to get to about 11, 12 seconds with this, if all goes well. Okay. So we run this, and I just want to confirm that it actually is using the right version. Yes, it's using the hacked big integer. That's good. And at the end, after some effort, it comes back at 15 seconds. So it's not exactly 4 times. In fact, it's about 3 times faster. But it's also not only twice as fast. Okay. Now, let's have a look at any questions, by the way. We can mix the questions up with the... I write a newsletter. Some of you are subscribed. If you're not subscribed, you can subscribe there. And if you are subscribed, you can say hello and ask questions at that particular special link just for you guys. Anyway, so I'll show that at the end again. Now, thanks, Andre. So Andre gets an award for reminding us to commit. Demo 3. Good. Now, what do we want to do? In fact, before I do I'm going to do another change before I do the go to number 4. And that is to actually print out how long each of the multiplications takes. So here we're going to say long time equals system.current time millis, and try and finally time equals system.current time millis minus time, and print out time. Now this is not really going to work. I'm just warning you in case you think it's going to work. It won't actually work very well because system current time millis is a system call. So if you call it all the time, it's going to slow down our algorithm quite substantially. So you'll see now that the output is going to be like, okay, right. So it's going to be very busy. Even if we say if time is bigger than 50, it's still going to take far too long to actually complete. Right. So what we're going to do instead is we're going to change this and say if n is bigger than, let's make it 10,000, then call system current time millis, otherwise just call it naught. And the same here, if n is bigger than 10,000, then call that, otherwise set it to naught. And now you can see how long each of the different things takes. Now, of course, 25 million will include all the other numbers it worked out to get to 25 million. So that's why the numbers are bigger. But you might notice something else here. Do you notice anything? Pardon? I'm working out the same thing over and over again. Okay? And it's the nature of the algorithm because we are doing this, but we're going, two numbers which are almost exactly the same. And so there's a very high probability of actually having to work out the same number repeatedly. And so that gets us to the next point, and we just commit that because that's actually quite a nice commit, demo 3 with timing. This gets us to the next point, which is you could also cache the results to avoid having to work it out over and over again. Now, you have to be very careful because we don't want to cause a memory leak. We don't use a static cache. We don't use a static map because a static map wouldn't have an easy way of being collected. All right. And what we'll do is we'll do this. We'll make a second method which takes as a parameter map of integer comma big integer. Cache, and we're going to make a cache up here, big integer. It has to be thread safe because it's going to be used for multiple threads. So it's going to be integer comma big integer. Cache equals new, wrong way around, sorry, map equals new concurrent hash map. And then I'm going to seed it, put naught comma 0, and 1 comma 1, and then I'm going to return f n comma cache. Now, a mistake that I've often made when doing this type of code is to forget to change all the places where I called f, especially if you do method overloading. So a simple trick is to change this name, and then it shows you where you need to add the cache. I'm sure you've done something similar. Okay, there we go. And then I change it back. Now, I don't need this beginning statement, but I do need to do this. I need to say big integer result equals cache.get n. If results is null, then I want to work it out. Only then. So I'm going to say results equals and results equals. I'm going to put it into the map over here, cache.put n comma result, and then return result. Okay. So this is how you can do it. And now I'm only going to work out each number a single time. Right? Wrong. Again, the nature of the algorithm gives you the probability, a very high probability, that you will actually want to work out the same number at the same time for multiple threads. But we do sometimes get a win, and we've managed to get our time down to 10 seconds. So we have managed to achieve something. All right. Now, this is demo 4. Before I go on, is there any better way that I could do this over here? The cache.get, and if result is null, then compute if absent sounds like a good idea. Put if absent, I'll show you one way of doing it with a special mechanism, but compute if absent looks like a very good idea to use here. Now, let's. Pardon? Yes, I'm going to commit that. Thank you very much. So let's do compute if absent here. So we could say return cache.compute if absent in comma key, and then you can just do this. You can say return. So you have to do cache.put, and you can just do like that. So who thinks this is better? Encoding style. Who thinks this is better encoding style? Who thinks this is worse? Why do you think it's worse, Andre?
Because it is very hard to test.
Hard to test, okay. Hard to understand? No, it's not. Compute if absent, it's a function. That's easy to understand. No, you're wrong there. Sorry. Any good reasons why it's bad? Yeah, the lambda is a bit too long. I do agree with that. Yes. That's a good point. Let's run it and see if it performs the same. And we've introduced a live lock, infinite loop, into our system. You see, something they don't really tell you, I mean, you can figure it out because it's kind of obvious if you really think about it deeply, but I didn't think of it when I started using it, is that compute if absent is not allowed to modify the structure of the map. That's sort of an implicit condition, which I don't actually say. But you're not allowed to do that. They call it a recursive update. This is a recursive update of the map. If you try to do that, it just hangs up. So you can't use it. Even if you like it, if you don't like it, either case, you can't use it here. So we're going to do, how do you do this? Get stash. There we go. Back to where we were. Brilliant. Okay, so we're back to where we were with cache.get. So we do want to do something like compute if absent, But we can't use compute if absent because that doesn't allow us to change the structure of the map. Okay, let's have a look at another mechanism we could use. And that is to, instead of using get and put, we could use put if absent. Now, there's nothing wrong with put if absent. That works quite nicely. You see, compute if absent is trying to verify, or it's trying to guarantee that the calculation is only called a single time. Whereas with put if absent, there's no such guarantee. So what we're going to do is we're going to put a special type of big integer into the map. And if we find that integer, then we know that somebody else is busy working on it. If we don't, then we can start working on it. So put if absent would return either null, or the placeholder, or the actual value. So let's do this. The first thing we're going to do is to make a big private void, final big integer reserved equals value of minus 1,000, so just some number which is negative, so we can see if we looked at it, we knew it was a reserve value. And then instead of saying get, we're going to say put if absent n comma reserved. We're also going to use the reserved as a lock. So we're going to say here synchronized reserved cache.put, and afterwards reserved.notify all to wake anybody up who might be waiting on it. So the first if is if it's null. That's the first case. That means we were the first to put reserved into the map. We won the race. We go to the calculation. The next if will be else if result is reserved. That means that somebody else put it in before us, and we now are going to wait for them to finish. We're going to say synchronized on reserved, and we're going to say while results equals cache.getN is equal to reserved, we wait. So we wait until it's not equal to reserved. And around this whole thing, we're going to do a try catch. And if we get interrupted, we're going to just throw a new cancellation exception. Interrupted. Right. So I've got a wait and I've got a notify. And this means that now I should only calculate every number a single time. And if you look at the output, you can see that that's exactly what's happening. Every number is only calculated once, and we've got a better performance too. 7.4 seconds. That's a nice improvement. This is our demo 5. So we're attacking this problem from lots of different angles to try and get the best performance. Now, when we run the code, at the beginning, if you take a few thread dumps, at the beginning, you'll notice that that at the beginning of the run of the 100 million, most of the threads are waiting. Waiting. In fact, here's only one thread is actually working. It's like one thread is doing some square, and the rest is just sitting around waiting. And so that, of course, is also not ideal. And that's basically where this diagram came from at the beginning, that at the beginning, it's there's a lot of black. Once the algorithm, once we have more calculations in play, the more different calculations at play, we don't have threads waiting for each other, and everything's good. But in the beginning, we have this problem. So this comes to the demo 6, which is the managed blocker. Now, the managed blocker is the way in which we can have blocking operations that are compatible with the common fork join pool, and with fork join. There are two classes at the moment that use managed blocker. the phaser, Java 7 phaser, which is a replacement for countdown latch and for cyclic barrier. And then there's also completable future is another class, Java 8 class, which internally uses managed blocker to keep the parallelism high. And basically, whenever you would block, whenever you would wait, you are allowing the fork join pool to perhaps create another thread to keep the parallelism at the same level. When you construct a fork join pool, you don't specify the maximum number of threads. You specify the desired parallelism. That's what you specify. You don't specify the number of threads. And so the desired parallelism is basically the number of active threads. So how many threads should be running at the same time? Now, fork join pool is mostly used for CPU-intensive tasks. That's why your parallel streams use fork join pool. They should be used for CPU-intensive tasks, not for IO-intensive tasks. Okay, so the fork join pool, if you do it, if you block together with the managed blocker, it allows the parallelism to stay high as well. Okay, let's try and add that. This is actually probably the easiest of all the examples. We take this waiting code over here, and this is going to become part of the managed blocker. So we're going to make it inside here a private class reserved Fibonacci blocker, for example, implements the managed blocker interface, which is inside fork join pool. It's got two methods, block and is releasable. And block basically becomes this. It becomes the same code as before. So the code, I've moved it, I've copied it from where I waited before down into the block. And the is releasable is basically your condition predicate, which is this thing over here, right? So let's negate that, and we're going to take this code out of here and put that into is releasable. So my block is actually complete. I don't need to do anything else for the block. Is releasable is the condition predicate that I was using to wait. And I need to have a big integer result, and I need to have a private, let's copy the cache and the int n from up here. Let's put that in here. Private final. And we did, of course, a constructor. So now I've written a complete managed blocker. It's basically taking my waiting code and it puts it into the block method. And then the only thing I need to still change is over here where I do my synchronize, and I'm now going to say my reserved Fibonacci blocker equals new blocker with the n and the cache. Then I'm going to say fork join pool dot manage block on the blocker, and then we're going to say results equals blocker dot results, like so. So I'm just replacing the previous wait code with this code. By doing so, I'm now able to use this within the fork join pool without causing myself major headaches. Okay, let's run it, and I'm just warning you that I did this demo a few times. It didn't actually run fast, it ran slower, so hopefully today it's going to behave itself. And please be faster. No, it's not faster. You see, the problem with doing the demo is that for small results, it is very, very slightly faster, but for small results, for small numbers of Fibonacci, you don't actually see a big difference because at the beginning there's not a large time of black. If you take a bigger number like 250 million or a billion, you'll see a much bigger result, but it'll take too long to run for the demo. So we'll be spending most of the time just waiting for the demos to run. So you can try it with bigger numbers, you'll see a bigger difference. and we'll quickly commit that as well. Demo 6. Now, I've got a seventh demo, which I'm not going to code. You're going to code that, right? That's your job. I do have a solution for it, and I'll give you some clues. So what you'll need to make this work with completable future is you'll need to use my hacked big integer, which you can get from a GitHub repository. Just search for in Riga on my list of repositories, you'll find it. You'll need completable future. You'll need to use, well, I would recommend you use the method then accept both async and the method complete. And you can, by doing that, you can actually get rid of the manage blocker because it's done automatically for you inside the completable future, and you can get rid of the reserved caching scheme. And so the idea is the following: that instead of having a cache that contains big integers, you're going to have a cache that's going to contain completable futures. Your main thread is going to set up the entire cache of calculations, and then in the end, you're going to join the values and give the result back. Now, something you can try it out with larger numbers. So don't just try 100 million, because 100 million completes too quickly. Try it out with bigger values like 1 billion to see how that performs. But also try out what happens if you try to disable the fork join pool. If you say common parallelism equals 0, see how that performs. And if you're interested, send me your answers here on that link, tinyurl.com, Riga 17. Also, if you want to subscribe to a newsletter or say hello, you're more welcome to do so. Do you have any questions? We've got a few, about 7 minutes left for questions, I believe. Okay, so the question is, have I done this with parallel streams? I wouldn't know how to. If you can figure that out, I'd be very interested to see. I've sort of thought of doing it with a splitterator, but the splitterator is really just it's ideally used for iterating and splitting at the same time, so for parallel processing of collections. It's not really for parallelization of algorithms. So I myself, I don't know how to, I wouldn't know how to do it. So if you figure out a solution, please send it to me. I'd be very interested to see it. And yeah. Any other questions? What is the answer for the first task? The answer for the first task, what do you think? So we had so those of you who were here 2 years ago, I had a chat to Ted Neward last week. Do you know if you remember Ted Neward's incident? Yeah, you do. So he recommended I do some shopping before I come here. And I was looking for some shopping, but I didn't actually get a chance to get what I needed. And luckily I didn't need it after all. So anyway, let's look at the print line. Print line fun. What is the output? Random? Why random? Because it's a parallel stream or why? Okay, maybe. So, if you go to my GitHub repository, which is Carbots, right? GitHub Carbots, you'll find all of these files, and you can try it out. Any more questions? If not, then I'm going to let you go for lunch quickly before the long queues start. You've got 3 minutes to get your place.
Monica Beckwith with her presentation, The Performance Engineer's Guide to How to Hotspot Virtual Machines Execution Engine.
Yes. Well, hello. I'm Monica Beckwith. I'm a JVM performance engineer. And thank you for Riga Dev Days for having me here. This is my first time presenting and first time in Riga. So I was very excited for the trip, except for the jet lag part of it, which usually happens right about now because it's about 5 a.m. my time. So I'm crashing slightly. But I hope to talk more about performance engineering and the hotspot virtual machine and trying to tie them together as to what optimizations have gone into the execution engine for OpenJDK hotspot or even Oracle's hotspot, which are similar. So, like I said, I'm a JVM performance engineer. I worked with Oracle and prior to that Sun Microsystems, and before that I was a compiler engineer and moved to JVM JIT compilation engineering at Advanced Micro Devices. So I've done performance for more than a decade, and basically most of it has been on hotspot virtual machine. I worked with the JVM heuristics. I worked with garbage collection, like the algorithm, as well as optimization of allocations, and then JIT compilation itself, like the generated code, optimizing the generated code on different architectures like x86, Spark. So that's about me. What I'm going to do today, like I said, I'm going to talk about performance engineering, the trifecta of performance, and the hotspot virtual machine. So the helpers in the hotspot virtual machine are what I call the execution engine and the runtime. So I'll talk about how performance impacts innovation in optimizations in the execution engine and runtime. The slide deck that I have is going to go over an hour, but what I'm going to do is kind of give the overview, and we may not be able to talk about certain optimization like compressed loops, which come later on in my slide, but the deck is complete, and you guys will have the deck to go over the slides later. And then eventually I would, like I said, talk about the various optimizations. So without wasting any time, I want to dive into the hotspot virtual machine. So we have your Java application, and that runs on the Java VM with the help of Java API, right? This could run on a virtualized environment in the cloud, wherever, but eventually it has to work on a hardware, and that's because that's where the JIT optimizations kick in, trying to optimize on the hardware that you're running on. Okay. Most of us know about the Java runtime environment. That's what we download off Oracle's website or from OpenJDK, right? So the JRE, which is the Java runtime environment, comprises of the Java API and the Java virtual machine. So the helpers that I'm going to talk about today, like I said, are the runtime and the execution engine. So let's quickly look at the execution engine. So we have the heap management, which is we call as garbage collection, and then we have the compilation, JIT compilation, and ahead of time that's in Java 9. So what is garbage collection? So many people know garbage collection as reclamation. You're trying to get your space back, trying to reclaim memory. But garbage collection, because it's memory management, it also involves allocation. So when you're thinking about garbage collection, don't just think about getting your space back, but think about optimizing allocations as well. And we'll talk about that shortly. What about compilation? So we all know static compilers, right? Like your favorite C compiler. But there is also ahead of time compilation. So when we talk about dynamic compilation, we're talking mostly about like JIT compilation in this particular case, which means just-in-time compilation. So it happens just in time when you need it. But ahead-of-time compilation can be very useful for shared code. So you can optimize and have this compiled code ready for use when you need it. So it kind of helps with startup time. So you don't have to do just-in-time if you already know that you can optimize libraries as well ahead of time. And the next two are what Hotspot has been using for a long time. And they're called the profile-guided optimizations and adaptive optimizations. And in my talk, I'll talk more about those shortly. So what about runtime? So we all know as the runtime as the interpreter, right? So at startup, you have, it starts in the interpreter mode, Hotspot virtual machine. But runtime also does VM class loading and a bunch of other things shown here. So we have the bytecode verification and synchronization, thread management. If you're more interested in the runtime, there's a link right there. It's available in the slide deck. You can read more about the runtime at that link. So as performance engineers, what we're interested in is the runtime goal, which is simple, converting bytecode into native code, right? So, and to achieve, how do we achieve that goal? How do we optimize getting from bytecode to native code is what performance engineers always strive to do. So now that we know, we have an overview of the Hotspot virtual machine, let's talk about performance and how we can tie them together. So if somebody asked me what drives innovation and performance, I would talk about the trifecta of performance. So basically it's responsiveness, it's footprint, and then throughput, okay? So what do I mean by responsiveness? If I send a stimulus, you know, how much time, how soon do I get the response? So basically if I want to write to my database, for example, so I send my write command, and how soon does it update whatever, right? So that's, in simple terms, is responsiveness. What about footprint? Footprint is the size of your application, data, everything on the system, the actual in-memory size of your application and data and everything. So as a performance engineer, I would want to optimize this. So the way I would optimize is maybe remove the redundancies and maybe compact, right? So how much more can I fit in? That's the goal always, is how much more can I fit in the space? And then the third one is throughput. How can I maximize operations per second? You know, I want to make sure that I am doing as many operations, like I'm utilizing all my cores and everything and trying to get in more operations per second. So that's the throughput goal, right? So now how do all three, the trifecta, how do they fit in with the Hotspot's execution engine? So let's start with responsiveness. So I'm going to talk about responsiveness with respect to the execution engine and the runtime, with respect to the Hotspot virtual machine. So in the execution engine, like I said, is garbage collection and compilation. So what about responsiveness and GC, garbage collection? So to improve responsiveness in memory management in Hotspot, we have faster allocation paths. We have something known as thread local allocation buffers, and I'll talk more about them briefly. So there's optimizations to improve allocations. There's also optimization to improve reclamation. So, and then we'll talk more about that. So I'm going to only cover three of the garbage collectors. There are more garbage collectors in Hotspot virtual machine. So I'm going to cover the throughput garbage collector, which is also called the parallel garbage collector. I'm going to talk about the mostly concurrent mark and sweep, which is also known as CMS, and then G1, GC, which is garbage first garbage collector. We'll talk about how the reclamation is handled differently in all three of them. And then the other way to improve responsiveness is to do more work concurrently. So most of the garbage collectors in OpenJDK Hotspot or this Oracle Hotspot virtual machine, they have stop the world pauses. So what that means is that all your application threads will come to a halt, and the garbage collectors will do their work, either compacting or whatever, or marking. And but to be able to to improve responsiveness, some of the work can be shifted to be done more concurrently. What that means is your application's threads can still work, and your garbage collection threads are working concurrently with your application threads. We'll talk more about the algorithms, how they handle that. Next is responsiveness and compilation. Okay, so I already mentioned about the startup time improvement that ahead-of-time compilation brings about. And then we have something called the adaptive optimizer. So most of your static compilation techniques, like vectorization and intrinsics, are also available in OpenJDK Hotspot virtual machine. But OpenJDK Hotspot also has something that is advanced inlining optimizations and other such optimizations, which I'll cover if time permits. And then, of course, locking improvements. Now, locking improvements, I put it here, and then I'll talk about it in runtime as well, because it kind of straddles both the spaces. It's compilation as well as runtime improvements. So like I mentioned, in runtime also, I'm talking about locking improvements. And the next one is class data sharing. So if you have not looked at class data sharing, it's only available with a couple of GCs. And what it does is, if you have code that's shareable, and it helps reduce with the startup time, similar to what I had mentioned with ahead-of-time compilation. So now we spoke about responsiveness, and then let's move on to footprint. So again, how do we reduce the size, right? So with respect to GC, of course, we have compaction, right? So what is compaction? So if you let your garbage collector run over, so basically you're allocating, you're promoting with the most of the garbage collectors in OpenJDK Hotspot, you have something called multi-generation. Basically, you have a young generation and an old generation, and as you age objects, they get promoted into the old generation. So over time, your old generation, if you don't do compaction, could look like a bunch of live objects, dead objects, live objects dead. So it could look like Swiss cheese. So some of the GC algorithms achieve compaction. What that means is kind of clubbing your live objects together at the lower end of the heap. Some garbage collectors in OpenJDK Hotspot do partial compaction as well, which is also known as incremental compaction. And in G1 GC terms, it's called mixed garbage collection. There are algorithm refinements in reducing allocations. So if you reduce allocations, you're kind of helping with footprint reduction as well. And the way we do it in OpenJDK Hotspot is either allocating depth first or breadth first, or other like escape analysis and stuff like that. And then we have compressed headers. So compressed headers is something that came with compressed object pointers. Ordinary object pointers. And I'll talk about compressed headers if we get some time. What about footprint and compilation? So inlining, first of all, is the most important optimization that OpenJDK Hotspot brings about. we have escape analysis that I spoke about, which looks if an allocation can escape from the method. And then we have something called de-optimization. Because Java has dynamic loading of classes, and so there's many times some things that were presumed to be hot more when it's profiled, it may not be true anymore. So then we need to be able to de-optimize that particular code that we thought was hot. So that is that can be done in Java, and that is called zombie code or de-optimized code. What about footprint and the runtime? I spoke about compressed OOPs and compressed class pointers. We have something called code caches, which stores your compiled native code, and then we have class data sharing. So let's talk about throughput and the execution engine now. So we covered responsiveness, we covered footprint, and now the optimizations that have gone into OpenJDK Hotspot to improve throughput. So looking at garbage collection, we have multi-threaded work stealing. So and one of the examples would be the Parallel GC. Actually, all garbage collections have multi-threaded work stealing, but the first time it was introduced in the old generation was with Parallel GC. What that means is when your application threads are paused and your garbage collection threads are doing the work, you can employ multiple garbage collection threads, and you can have work queues, and they can perform something called work stealing. And there's a protocol called termination protocol. So this is highly advanced, and it's basically all your queuing theories and stuff like that are implemented. So that helps with throughput, so trying to get the work done quicker. Then we have multi-generation again. I briefly covered it earlier. So most of the garbage collectors in OpenJDK Hotspot have young generation and an old generation, and I will talk more about that. So that helps with throughput because now you can age objects and only promote when necessary. Multi-phase marking again, so you can divide. So marking doesn't need to be a long stop-the-world pause. You can do it, some of the work concurrently, some of the work can be done in different stages. So that helps with throughput as well. And I mentioned about compaction, either full compaction or incremental compaction. So what about throughput and compilation? So we have the JIT compiler, of course, right? So the just-in-time compilation helps with throughput. And then we have intrinsics. Basically, these are hand-optimized code that help with throughput, because now you're going to an optimized level of code instead of just using a generic optimization. Vectorization, again, for SIMD instructions, multiple data, single input, multiple data. These are with x86, there's a lot of SIMD instructions. So a hotspot can use vectorization. It's not very advanced. It's in infancy. So if you're used to static compilers and you're used to vectorization, don't expect the same out of hotspot, because again, it's a dynamic compilation. And think about how intrinsics with static compilers are kind of much easier, right? So with dynamic compilation, vectorization doesn't. So I may be covering and talking briefly about what Hotspot does right now, but I'll also include a link to the paper that the optimizations are based on. Okay, and then loop unrolling, of course. What about runtime and throughput? Of course, we have compressed OOPs. We already covered that, and then compressed class pointers. So that both of them help throughput. So now let's dive into these optimizations, okay? The first I want to cover are the garbage collection facts, and then the innovations based on the throughput and responsiveness and footprint. So, so the way the garbage collection evolved in Hotspot was because of throughput and latency pressures, right? So they're the two main drivers, and footprint kind of took a back seat. So throughput and latency are the two main drivers for refinement of GC algorithms. Almost all GCs in OpenJDK hotspot are generational. We have Shenandoah, which is not generational. And then, all right, so if I put all those things that we discussed earlier and we had clubbed them individually, if I put them all together, so we have the responsiveness column there, then we have the throughput column, and then we have the footprint column, okay? Another way to look at that would be, so another way to look at that would be if I could explain each of them and kind of put them together with respect to the GC algorithms, and that's what I'm going to do now. So let's first look at the multi-generational heap, right? So like I mentioned, we have the young generation and we have the old generation. So the young generation further has the Eden space and the survivor spaces. So here I've shown the same thing again. So, but here now I can talk more about how allocations happen. So, okay. Okay, so allocations, most allocations happen in Eden space, okay? And then after you age the object, so when a collection happens, most of the live objects will be moved, or all the live objects actually, will be moved to the survivor zero space, which is also known as 2 space, and the other one is called the from space. So at any given time, S0 and S1 will be either 2 or from. So as the objects are surviving, and they're also aged, so there's an age counter, which tells the age of these survivors. And once you cross the age threshold, those objects can be promoted, which is also known as tenured. Okay? By promotion means they'll get moved to the old generation. And then old generation collection kicks in. So if I, again, like I said, if I put all those optimizations into this particular format, so the faster allocation paths belong to the allocation area of the memory management. Multiple threaded work stealing belongs to the reclamation path. Faster reclamation also belongs to the reclamation. And now the reason I'm going to say allocations and promotions together, because some of the optimizations, like T-labs, also apply to P-labs, like promotion local access buffers, right? So that's why, it's not fair just to say allocations, but also for promotions, those techniques help. So you have multiple generation, which helps with the promotions as well as reclamation, and more work done concurrently, multi-phased marking, incremental compaction. So those things are basically different areas of optimizations within memory management. So let's talk about allocations quickly. So like I mentioned, multi-generation heap as well as faster allocation paths belong to allocation group. And then, and we also spoke about how most allocations happen in the Eden space. So, okay. So, and we also spoke about T-labs. So here are different ways that people refer to T-labs. They call it lock-free allocation. They also call it fast path allocation. There's also the slow path allocation. So, so these are different terminologies. So if I had to explain T-labs in a very simplified manner, each allocating thread has a T-lab. So, and then the Eden space is divided into this T-lab areas for each thread. They're not, at the very beginning, they're similar sized, but they get resized based on your allocation the threads allocation pattern. So for example, if I had 5 threads, you'll see 5 different TLABs. Okay, and as your allocations happen, your Eden gets full, and then at the first collection, the young collection, you will see that your survivor space gets filled with surviving objects. Eventually, they get promoted after aging, like I mentioned. So once your old generation is full, then we have old generation collection. And these collections are also called reclamation. So there are different terminologies, but they kind of mean the same thing, because you're reclaiming the heap. For reclamation, as I mentioned, there are lots of optimizations, such as the multi-phase marking, but the algorithms also differ, okay, especially for old generation collection. So we talked about Eden, survivors, young generation, old generation. So let's talk about the algorithms. So all generational OpenGDK hotspot garbage collectors have similar algorithm for young collection. So it's the same. It employs multiple threads. It stopped the world, and it's the same for all 3 that I'm going to cover today. But the old generation has different garbage collection algorithms. Okay? So we'll concentrate more on that, and that's what determines if it's a parallel collector or a CMS or a G1GC. It's not the young generation collection, it's how the old generation is reclaimed or collected. So for parallel GC, which is also known as the throughput collector, I call it the throughput maximizer, these are the optimizations that went in. So when I talked about innovations in garbage collection, and I talked about multiple threads, multi-generation, compacting collector, and faster reclamation via PLABs and TLABs. So those are the things that help throughput GC, called parallel GC, achieve better throughput. So it doesn't. What you don't see here is anything done concurrently. So there's no concurrent work. It's all stop the world. The next is latency-sensitive GC, is what I like to call it, but people know it as CMS, which is mostly concurrent mark and sweep. And what are the optimizations that went into CMS? The multiple generations, of course, because we have the young generation and the old generation, and then the multi-threaded workers. Okay, but the most effective are the next 2. Which there's one that you don't see, and that's the most effective one. So more work is done concurrently. That's why it's called mostly concurrent mark and sweep. And then the multi-phase markings, like I said, that's what the work is done concurrently. What you don't see here is compaction, and that's the most effective, and that's why it's latency-sensitive garbage collection. So CMS doesn't do compaction. What happens with CMS is the old generation does in-space deallocation for objects that are not live. Eventually, over time, it will lead to fragmentation, and then there's a fallback garbage collector, which is similar to what you may have seen with serial GC, which is a single-threaded compacting collector. So that's how CMS achieves its latency sensitivity, is by not doing compaction at all, just quick in-space deallocation. Okay, so G1GC is somewhere in the middle. What G1GC does is everything that's on the left. It does multi-generation heap, it has multi-thread workers, more work done concurrently, multi-phased marking, also has incremental compacting. So it doesn't have the drawback of CMS where eventually you'll have fragmented heap or concurrent mode failures. G1GC doesn't have that. And the way it combats the full stop-the-world pause of old generation collection in parallel GC is by pausing incrementally. So you have multiple thresholds in G1GC where you could say that I only want my heap to be filled up to, like, say, 95% or whatever. And then there's like the marking threshold where you say, as soon as my heap crosses 45% occupancy, start the marking cycle. So there are multiple thresholds which help you determine how soon you want the incremental collection to start happening, and how many incremental collections do you want, and what makes these incremental collections more helpful is having a pause time goal. So G1 does have a prediction logic where you can give a hint saying that I would like my pause time to be 200 milliseconds. It's not a hard stop, so it'll try to achieve 200 milliseconds. And that kind of, with the help of prediction logic, over time you will see that if garbage collection is tuned well, then your application will try to behave as the way you desire it. So it'll try to achieve your pause time goals over time. So those are the three hotspot GCs that I was going to cover. Then we'll move on to compilation engines and the optimizations in the compilation engine. So like I mentioned, adaptive optimization and profile-guided optimizations are the two optimizations in the for hotspot virtual machine. And again, putting all the three tables together, we have all the optimizations or major optimizations that are in the hotspot compilation engine. We may be able to cover, we'll definitely cover all of them, so I'm just going to say these are the ones that we're going to cover mostly within the time that we have, which is only 13 minutes. Wow. Okay. So how does hotspot achieve JIT compilation? So there are counters. Okay, hotspot starts in interpreter mode, and there are counters that count loop backs, so loops basically, and then you have method entries. So every time you have the same method is invoked again and again, the counter increments, and then same goes on as the loop. So once these thresholds are crossed, so there's something called compile threshold. So once the threshold is crossed, then that particular method, which is supposedly hot method, is compiled. That's called just-in-time compilation with profile-guided compilation. You could also have on-stack replacement. So for those hot loops, like I mentioned, you could choose to just optimize those loops, and you can replace them on stack. So that's why it's called on-stack replacement. So OSR is what is the compilation lingo. So prior to tiered compilation, hotspot used to have C1 and C2, also known as client and server compilers. So the difference was that this client compiler was very helpful in decreasing your startup time. It's because it did very few optimizations, right? So it was working. It starts an interpreter, and the compilation threshold was very low as well. So you start compiling with client compiler, but there are not that many optimizations. With C2, also known as server compiler, it's the same way. You start in the interpreter, but the compilation threshold is very high. So if your application has a bunch of hot methods and they cross that threshold, then that's the only time they would be compiled. So, and then C2 includes a lot of high performance optimizations. So I think with JDK 8, we had tiered compilation, which kind of, I think it may have been in JDK 7 too, but it wasn't enabled by default until JDK 8. So, of course, so it helped improve startup as well as your long-running server application compilations as well. So tiered compilation has 5 different levels of compilation. So It starts in interpreter, and then there are 3 levels of compilation at C1, which is the client compiler level. So first, the C1 will have no profiling, and then the second level of C1 would have the loopback counters and the method entry counters. And the third one is like full, C1 with full profiling. And eventually it goes to C2. So the last level is C2. So those are the levels in tiered compilation. One thing to note with respect to, because I was talking about code cache earlier, how it helps with footprint and everything. But one thing to note, with the introduction of tiered compilation, it has some effects on code cache. So basically, the code cache gets bigger or needs more space. And like I mentioned, code cache is where your compiled native code resides. So when I talk about compilation threshold, is right after that point, things will start getting compiled. Now with tiered compilation, the first level of compilation threshold is only 100 invocations. So if your method has 100 invocations, it'll get compiled. So imagine how much of a bloat that does on your code cache. And then when the performance engineering team was studying the effects, we found out that code cache needs to be 5x larger, 5 times larger than what it used to be for non-tiered. So now, with JDK8, the default changed from 48 megabytes to 240 megabytes. So if you need more, then you can use something called reserved code cache size. You can change your code cache size based on using that particular option. So now let's talk about the advanced optimizations, also known as adaptive optimization. So you start up in interpreter, and then you have profiling of hotspots, critical hotspots, trying to figure out which ones to compile or not. And then you have you start doing chit optimizations. But there's something called de-optimization. Okay, and then you could eventually, because of de-optimization, you can probably go back into interpreter mode. Okay, so let's talk about that. So basically, de-optimizations are your oopsies. Like you did something, and then you want to take a step back and say, I didn't quite want to do that, and Hotspot does that. So you could have dependencies in validation. You could have class unloading, like I said, because of the dynamic class loading. And then you may have taken some uncommon. You thought that this method was hot, but all of a sudden it's not quite hot. So you optimized it, but that path was only taken for, say, 100 invocations or whatever, right? So also your profiling information could be wrong, because like I said, you took an uncommon path and then you got the wrong information. Usually I have an example because Hotspot does provide options on how to look at your print compilation details. So you can look at that and it'll tell you that your code has been zombied or the code has been de-optimized from a level from level 2. So when you're changing the levels of tiered compilation, you're going from 2 to 4, for example, the code that was at level 2 has to be de-optimized and then collected so the code cache pressure can be relieved. So I don't have that now because I don't have much time. So moving on to escape analysis. Like I mentioned, it's very simple. It's trying to find out if your allocations can escape. So how do we do that? So we're going to make sure it's not stored to a static field or non-static field of an external object. It's not returned from the method, of course, and not passed as a parameter to another method where it can escape. So if I had to put it together as, so basically, if it's allocated, if the allocated object does not escape the compiled method and allocated object not passed as a parameter, then you can remove allocation and keep the field values in registers. And if the allocated object doesn't escape the compile method, but allocated object is passed as a parameter, then you can still remove some locks associated with the object and use optimized compare instructions. That's what the JIT does internally. Okay? How about runtime innovations? So I have 5 minutes. I'll start with it. We may not be able to finish it, but we'll start with this one. So again, putting all the tables together, we have, so we'll talk about compressed tubes and compressed class pointers. And we already covered code cache, so we won't talk about that. So we have a Java object, and all of us know the Java object has header and body, right? And a couple of things to know before we talk about compressed tube optimizations. Objects are always 8-byte aligned, and that's the reason why we can do optimizations like compressed tubes. Fields are aligned by the type. Fields can fill a gap that may be required for alignment purposes, and are accessed using offsets. All fields are accessed using offsets from the start of the object, okay? So this is important just because when I show you the layout, the object layout, you need to know how fields are accessed. And anyway, so this is an important bit of information here. So I used a tool called Java Object Layout, JOL. It's to analyze Java object layout, of course. And this is the instruction that, so I wanted to see the internals, basically field layout and contents and object header. And I wanted to show what compressed oops and compressed headers, how it is achieved within the object. So let's first look at compressed class pointers with 3-bit shift. And basically 3-bit shift is where, that when I talked about object alignment, 8-byte align, that's the 3-bit shift, okay? So what does a Java header, object header have? So it has the mark word, and then we have the class pointer, right? So it's the size of your native pointer. So if you are on a 64-bit system, so the class would be your 64-bit, like the pointer would be 64-bit. So, and then if it's an array object, then you have array length as well as a part of the header. So if I wanted to look at the uncompressed object layout, it would look something like that. So I looked at 8-byte array, and what you see here are the first 2 lines with size of total of 8 bytes is your mark word. Okay, and then the next 2. So if you see, you can see the object headers. The first 5 are object headers. So the next 2 are your class pointer. Okay, and then the next one you see is your object header right there as well, and that's your array length because it's an 8-byte array. All right, so you see the array length as in that next 4 bytes. And then you have something called alignment padding. Remember I mentioned that sometimes you need to maintain alignment, you can do padding. So that's what is done here. That's 4 bytes. And then, of course, the next one is your byte array. So when we see the same thing with compressed oops turned on, what you can see is the mark word is the same. And then you have the next one is only 4 bytes. And remember, it was 8 bytes earlier. And that's your compressed class pointer. So that's how you can visualize. So that's what happens. So basically, instead of 8 bytes, now we just need 4 bytes. And that's the compressed class pointer optimization. And then, of course, everything else is similar. This is your array length. And then the next is 8 byte. What you see also missing here is the alignment. Remember, in the uncompressed stage, we had the alignment issue, so we had to have some padding. Here, you don't see any padding. So if I compare them side by side, what you see is that the compressed one needed 24 bytes, and the uncompressed one needed 32 bytes. So, of course, 4 byte was because of the alignment, but also the other ones was because of the compressed class pointer, right? So we save about 8 bytes. Okay, so going back to the optimizations, what about compressed OOPS? Like, how do you visualize compressed OOPS optimization? So for that, I'm going to still use Java Object Layout, and I'm going to look at class. So JOL of a class. So you can see that you see the offset on the left. It's the same thing. Offset on the left, and then the size, the type, the description, and the value. So in this particular case, it's 168 bytes, the instance, okay? So the first one is the object header, which is 16 bytes. And if you go dive deep into that, you'll see the offsets again and the size. So just looking at the size for now, when you look at the same thing with compressed, enabled, you see the size has changed. Now the object header is only 12 bytes instead of 16. It's only 12 bytes, and the size of all those the class.module, class.name, all those have changed to 4. So basically, that's what compressed OOPS enables. It enables you to go from 8 bytes down to 4 bytes because that's all you need. So it's by achieving the 3-bit shift. So you're not using the 64-bit pointers. You're using only 32-bit pointers, okay? So we achieved compressed class as well as compressed OOPS shift. So I was talking about the 3-bit shift all the time, right? So if you look at the optimization, this is what you will see. So the wide ordinary object pointer, which is your regular 64-bit pointer, can be changed into a narrow OOP, which is your 32-bit pointer, by shifting, by 3-bit shifting. And then, of course, since all fields can be accessed by the offset, then you have something called the field offset, okay? So if I put it in a tabular form again, so if your heap size, and within compressed OOPS, there are various optimizations that can be done called zero-based OOPS and stuff like that. So if your heap size is already less than 4 gigs, you don't need any encoding or decoding because your wide OOP is your narrow OOP because it's 4 gig is basically addressable by 32 bits, right? So now if it's it's more than 4 gigs but it's less than 28 gigs, you can do something called zero-based. So all you need is your narrow OOP can be shifted by 3, okay? Then between 28 and 32, you have your regular optimization, which is what I had shown earlier. And then with, I think, JDK 8, you can also go a step further and change your alignment. Remember, by default, the objects are aligned on 8-byte boundaries, right? So if you change the alignment, then you could achieve even more addressable space. And in this case, if you see, the shifting has changed from 3 bits to 4 bits because we changed the alignment. So kind of putting it all together again, you see if it's less than 4, you don't need any shifting. If it's between 4 and 28, you shift by 3. Even if it's less than 32, you shift by 3. But if you want to go to less than 64, if you think that compressed OOPS are going to benefit you, then you change the alignment and to 16 bytes, and then you change the shift by. Actually, it automatically will do that for you. So JDK 8 does all this automatically. And that's pretty much it, I think. I went really fast, I know, and I'm sorry, but I had a lot of optimizations to cover, and I'm open to questions, if you have questions. Okay, yes.
How does adaptive sizing work?
Hmm?
How does adaptive sizing work?
Adaptive sizing?
Yeah.
In
Like in the throughput collector.
Good question. So I think it's disabled now. Okay. So this is very interesting because when prior to adaptive sizing, what used to happen is that we could only grow the young generation up to X, and then because right after that we had the old generation that needed to start. So the young generation could never go beyond a certain point. But now, with the introduction of adaptive sizing, you have this kind of buffer space. So between the young generation, because remember, heap is contiguous. And before G1, GC, the young generation and the old generation were right next to each other. So there was a padding. This was an open space, which the old generation could shrink, in a way, not shrink, but add to, or it could be reclaimed. It could be claimed by the young generation. So you have young generation, this padding, and then old generation. So that's how adaptive sizing works. So by default, that space could be either claimed by either of them, but because of the complexities in the algorithm, when we turned on adaptive sizing, we found out that it doesn't work adaptively. It's always that I think young generation used to reclaim that space, and and it would never give it back, even if the young generation never grew. And there were lots of other issues. So for maybe about 10 builds, we had enabled it by default, but we have turned it off. And I don't even know if the code is still maintained or not, but that's basically it. It's this hollow space between the young generation and the old generation where you could any one of those could either shrink or grow into. Yeah.
Regarding the garbage collector stages, which of the step or stage causes the stop the world pauses percentile?
So so when we talk about generational collectance, the reason I'm saying this because there is Shenandoah. So if we go back to the world before Shenandoah, all the OpenGDK hotspot were generational. So when you talk about young generation, all young generation collection in those garbage collectors are stop the world. Yeah. Okay, all of them. Now the difference that is brought about is by the old generation collection. So for throughput, the old generation collection is full stop the world. So when I say full compacting, that means it stopped the world for everything, for marking and sweep and so MSC is the term, mark, sweep, compact. So it's a stop the world for mark, stop the world for sweep, stop the world for compact. Then comes CMS, where it does mostly concurrent mark, as the name implies. So some of the marking phase is concurrently done. Some of it is done in stop the world format. So, for example, remark, is stop the world, and initial mark is stop the world. So some of them are stop the world, and then the sweep is done independent. So you can sweep just because it's in space. It's like you reclaim this, and it goes into this kind of free list. So it's just a pointer to the free list, saying free list says, okay, this space is free, this space is free, so now the next promotion can go into those spaces. So there's a free list in CMS. And in G1, GC, again, the collection, which is the compaction, is the main thing, is stop the world. So G1, GC, the marking phase is similar to CMS, whereas some of it is concurrent and some of it is stop the world. But the collection is always stop the world, and the compaction is stop the world, in partial or fully.
Is it possible to achieve like compaction without the stop the world?
Yeah, I mean, there are lots of algorithms that do that, yes.
Okay, so if you have some questions else, you can ask them on 6th floor. There will be a press conference with speakers. And also, please vote about this presentation and others using Riga Dev Day app. Yep.
Okay.
Thanks.
Thanks. Thank you.
Okay. Hi everyone, I'm Andrei Pangin, the lead software engineer at Odnoklassniki, one of the largest social networks in the world, and probably the largest one running Java. My today's talk is not about just random facts. I will discuss problems that arise at Odnoklassniki as well as all other projects all around the world. I often hear Java developers asking about heap dumps and stack traces. This today's talk is inspired by the questions asked on Stack Overflow. This is just a small portion of them answered by myself. So I guess I shouldn't explain what stack trace is. Every Java developer saw it when he or she makes the very first mistake. So let's go directly to the demo. Here is a small program with a method that checks if an array is sorted or not. I run this method many times in the loop, but I made a typical off by one mistake here. I forgot -1. So what will I get there? Right. Array index out of bounds exception. But what the hell? Why I see the exceptions without a stack trace? Here, in the exception handler, I call print stack trace, but where is my stack trace? Who knows? Okay, let's see. Let's run this the same example with the following option. It's a JVM flag, meets stack trace in fast throw. Here are the exceptions again, and yeah, here are all our stack traces. There is an optimization in hotspot JVM that doesn't generate an exception stack traces for implicit exceptions thrown from a hot code. The same applies not only to array index out of bounds exception, but for other implicit exceptions as well, like null pointer exception, arithmetic exception, and so on. If such an optimization exists, there must be a reason for that, right? Maybe it makes the performance faster. Let's see. Here's a primitive benchmark I wrote to measure the cost of creating a simple object like Java util date with the exception object. I use a GMH micro-benchmarking framework. It helps to avoid common benchmarking pitfalls like warm-up, JIT optimizations, and so on. Look, it takes just 8 nanoseconds to create a simple object, but 150 times more to create an exception. Other exceptions are really expensive. Why? In fact, it's not exception creation that takes time, but rather collecting a stack trace. Each constructor of an exception calls fill-in stack trace method, which in turn results in a native method call. But good news is that this method is not final and it is public, so we basically can override it. So let's run our benchmark with an empty fill-in stack trace. Yeah, now we see that exception is as fast to create as a simple object. There is also another way to create fast to instantiate exceptions. There is a special protected constructor which accepts additional arguments. If we set writable stack trace to false, then exceptions will be again fast to create. Good. Now we know that. Now we know the exceptions, the cost of exception creation. Let's measure the cost of catch, throw, and catch. This benchmark calls some method recursively, and at the given depth, it throws an exception. Here are several interesting outcomes from the benchmark scores. First, we see that with just one method call, the try catch basically costs nothing. It is explained by the fact that hotspot JVM can inline one recursive method call, and if the catch clause is in the same context as throw, then throw will be as fast as the simple goto. The second interesting fact that on a deeper levels, the cost of throw catch is roughly proportional to the stack depth, which is quite understandable because it takes linear time to find an exception handler and to walk the stack trace. Let's go on with exception measurements. Filling stack trace just collects stack trace in some internal representation. But in order to print the stack trace or to send it somewhere, we need to convert it to a Java representation, an array of stack trace elements. So let's the measure get stack trace call. Wow, it appears to be more than 10 times slower. So not only the collecting stack trace takes time, but also converting it to a Java representation. Why it is so slow? Let's look into JDK source code. Here's the implementation of getStackTrace method. And we see here loop, and for every frame, there is a native method call, which results in a stack trace element object creation with a number of fields there. Note, there will be even more fields in stack trace element in Java 9 related to modules. And here is a surprise for those who parses traces with regular expressions or so on. Be prepared that your parser will be broken because the format has changed in Java 9. What we've seen is that exceptions themselves are just regular objects. What takes time is collecting an exception stack trace. And this time is linear depending on the stack depth. Throw is also cheap if the catch, if the exception is caught in the same context. Note that the context can include several methods due to inlining. Otherwise, throw performance also depends linearly on the stack depth. And a few recommendations on how to use stack traces. First of all, turn off this ugly JVM optimization. It will really help you in production to debug weird null pointer exceptions and so on. It is usually a bad practice to use exceptions for a normal control flow. However, in some rare cases, it can really help. For example, in a visitor pattern, when you want to return from a loop which in outer method. And in this case, prefer no stack trace exception with no stack traces. That's all about exceptions. In what other cases do you need stack traces? Your variance? Well, the basic use of stack traces is to see what an application is doing. JStack utility can dump all threads with their stacks and basic information about thread, like thread name, priority, and so on. What is interesting here is an ID. It is the native thread ID given by the operating system. For example, if you see top utility to find which thread takes the most CPU time, then you may match the top output with thread dump by this NID. We also see in this thread dump that thread 1 is waiting for some reentrant lock, but there is no clue which thread holds this lock. However, there is a less known JVM option that allows you to print this information. Here additional lines appeared saying that thread 2 holds this lock. You may be interested why this option is not enabled by default then. Well, for each reentrant lock, hotspot knows which thread is assigned to this lock, but there is no the reverse mapping. So in order to find all the locked reentrant locks, hotspot needs to traverse the whole Java heap to find all such locks. And of course, this takes time. Okay, another popular case that relies on exception stack traces is logging. Imagine an application that prints some warning message. This message can be actually printed from anywhere in the code, but you want to know from which place this message is printed exactly, preferably the file name and line number. In C language, there are preprocessor markers, file and line, but there is no such markers in Java. The only way you can achieve this information is by looking at the stack trace. So this is typical solution how logging frameworks get the location information. But as we know, the get stack trace call can be really expensive. Is there a better way? One may think that threads get stack trace can be faster because it doesn't need to create an exception. Who thinks it is faster? Or maybe slower? The same? Yeah, actually there is no magic. Threads get stack trace method also creates an exception. However, there is a secret method to get this location information faster. There is an interesting class named shared secrets in JDK, and it can access not the whole stack trace, but the particular stack trace element from this exception stack trace. So we don't need to convert all stack trace elements, just the element we need. The bad news is this won't work in future versions of Java, because the all stack working mechanism was completely rewritten in Java 9. That's the usual thing that happens with private APIs, so don't rely on private APIs unless you have a backup plan. Besides logging, there are other cases where method behavior may differ depending on who calls this method. For example, class for name may find the class or throw class not found exception depending on the class loader on the callers class loader. The same is true for getting resources or loading libraries. Access control do-privileged method may succeed or fail depending on whether it is called by trusted or untrusted code. If you are to write caller-sensitive method by yourself, how do you know the caller? The only way to know it, again, by obtaining a stack trace. However, there is a faster method. Note that it is also in undocumented private API. But this API will be still there in Java 9 because there is already a lot of code, production code that relies on this call. So it was decided to leave this method in Java 9. However, it will be likely removed in Java 10 or so. Okay, we've seen a number of use cases where standard stack walking API doesn't work. Ideally, there should be a completely new API that allows to work only a limited number of frames, for example, top 10 or so, to find frames only matched to the given criteria. The information should be obtained lazily. For example, if you don't require file name and line number, why spend time getting it? To meet these requirements, Java community came up with a brand new API in Java 9. And it is already known that it will be a part of the standard. This API is called Stack Walker, and it's really powerful, just like another known walker. At the same time, this API is quite simple. Just call this method to get an instance of Stack Walker. There are a few options to modify the default behavior. I will talk about these options a bit later. And another overridden version that is optimized for the given stack depth. Okay, what can we do with a stack walker? We can basically iterate through all frames and, for example, print them. If we add show reflect frames option, then a few more methods will appear in the stack trace, methods related to reflective method invocation. Another option, show hidden frames, yields yet more detailed stack trace. Show hidden frames also implies show reflect frames. And here is the central method of this new API. A scary signature, right? With lots of generics. But it's rather easy to use. Inside walk method, there is a stream, and this is just a regular stream of stack frames, and you may use it whatever you may do whatever you want with it. Skip frames, filter them, map, and whatever you can do with a regular stream. For example, if you need caller stack frame, you can do a thing like this. But there is also a shortcut method to get a caller class. Note retain class reference option. Without it, you'll be able to access just a caller class name, but not the class object. Here's a bit more complicated example. Here we get top 10 frames whose caller belongs to org Apache package. But why the signature is so tricky? Why not just a method that returns a stream of frames? Any ideas? Okay, imagine that API just returns a stream of frames. We can pass this stream to some another thread, forget it, and after several hours, invoke methods on this stream when the original stack trace is no more and original thread is already dead. Of course, the key point of the original API design, the laziness of its method, will no longer work. So the key idea of this tricky signature is to make you work with the stream inside a walk method, while the original stack trace is frozen. So you basically can get information from this stack trace lazily. And here is a bonus for you. No one from Oracle will tell you about this API because it is non-public, undocumented. It makes possibly not only get classes and methods from a stack trace, but also local variables, info, monitors, and even expression stack. Let's see an example. Okay. Here's a labyrinth program which searches an exit from a square labyrinth using a recursive method. When it finds the exit, it dumps the current stack. It starts with the cell 99 and tries to get to a cell 00. That's right. Okay, if we use a regular dump stack method, then of course we get a stack trace with the same methods. Of course, it is a recursive method. But if we change it with our stack trace dumper, which uses live stack frames, you'll be able to get the values of local variables at each method call. And here you can trace the whole path to the labyrinth exit. Here's how this stack dumper looks like. It gets a stack walker from the live stack frame method, from the live stack frame interface, sorry. And for each frame, it prints the frame itself and the locals, which we get using getLocals method. Note that all the methods are called using reflection because the interface is package private and we can't access it directly from our application. The other bad news is that we can't use actually reflection on a system classes in Java 9 unless we explicitly add this ability using the JVM option it opens. Okay, we can't talk about stack traces and not mention recursion. Let's have some fun with the recursion. What will happen if I run this program? Stack overflow error, right? But how much frames can I construct before I get stack overflow error? Hundreds, thousands, millions? Well, let's measure. So we catch stack overflow error and print the depth. 24,000, 30,000. 24 again. Each time the number of frames is different. 23, it can differ significantly. What can be the reason of this difference? Any ideas? Okay. Yeah, that's how recursion looks like. The clue is the background JIT compilation. Originally, the execution of methods started in interpreter, but after a certain number of invocations, the JIT kicks in and start compiling, but it compiles in background thread. And while compilation is working, the execution continues in interpreter. And as soon as compilation finishes, the next invocation switches to compiled version. Since GDK 8, when tiered compilation is enabled by default, there are even two compilers in hotspot JVM, C1 and C2. And of course, compiled methods are use less space on stack because they don't require they're not required to put everything on stack. For example, they can cache some local variables in registers. C2 compiler is even more optimizing, so its stack frame is yet smaller. And due to concurrency issues, there can be different number of interpreted and compiled frames each run. And that's why the number of recursive calls is different. I ran this test with the default stack size, which is 1 megabyte on 64-bit platform. Of course, the larger the stack size is, the more calls I can do. There are JVM options to modify the default stack size, and not everyone knows that there is a thread constructor that can change the stack size of an individual thread. But why on earth care about stack sizes? For bloody enterprise applications, of course. You see here just a single line of business logic, and everything else is boilerplate of frameworks, frameworks, frameworks. The last but not the least use case of stack traces is profiling. The idea of sampling profiler is very simple. The profiler wakes up every small period of time and collects stack traces to see what application threads are doing. And this is a really lightweight approach, so it is suitable for production. Let's see how it works. Here is a demo that I want to benchmark. It does many things. First, it generates some random points. Then it calculates distance from this point to some another location. And finally, puts this distance to a map. From the first sight, it's not obvious which will take the most time. It can be location generation, it can be mathematics, and it can be distance, a hash map operation. So let's measure using a standard benchmark, standard profiler, which comes with regular GDK package, Visual VM. Hey, where are you? It can't find my application. Okay. Let me try again. Here it is. Choose sampler, CPU, let it work for some time. And what I see in a sampling profiler that almost 100% time is used by system identity hashcode method. This doesn't look true for me. I don't think that almost everything is used by system identity hashcode. Why the profiler can lie? The problems originate from JVM's method of collecting thread dumps. Hotspot JVM cannot get stack traces at any arbitrary point. It can collect stack traces only at known positions in the code known as save points. Usually the save points are located at the ends of the loop and at method exits. The other problem is that JVM cannot distinguish native method that is blocked on some system call from a method which actually does some work, because all threads are measured equally. This is not a problem of a particular profiler. Many other popular profilers also suffer from the same problem. But Hotspot JVM has an undocumented API. Yeah, it has a lot of undocumented APIs, which can take thread stacks, not only at save points, but almost at any time. So the idea of using this API is simple. We catch timer signals from operating system and call this method to collect the stack trace of a thread that is running. And originally, this API was invented especially for Oracle Server Studio to give it competitor advantages, maybe. But since hotspot sources are open, we can also use this. People noticed such a treasure, and so did I, and implemented this approach in my async profiler project. And here how the output of async profiler looks for the same example. You know that, see that system identity hash code is somewhere in the bottom, and what takes the most time is actually a maths function. As a bonus, this profiler shows not only Java code, but the native code as well. Now we know the benefits of stack traces. Let's see how to get them efficiently. We can dump threads right from the same JVM using convenient Java API, which returns a stack trace in Java representation. For a more compact representation, there is another function provided by JVM tool interface. It returns an array of JMethod IDs. If any one of you has ever written some JNI code, then you know what JMethod ID is. This is also a much faster way to get stack traces. If you wish to get stack traces of a different process, then the fastest way is to ask virtual machine to dump the stack traces by itself. You need just to send a quit signal to it using kill -3 or so on. And JVM will execute the command by itself, and it doesn't create any Java objects or intermediate structures. It just walks through all threads and prints them to standard output. The same can be achieved by gstack utility, but the output will be redirected to the gstack console. You might know that gstack has a special forced mode. Though the output looks similar, actually these are two completely different utilities, and they involve completely different mechanisms. Let's see. gstack without F involves a dynamic attach mechanism, which works as follows. gstack creates a special file at the current directory with the process ID of the target JVM and sends a signal to the JVM. JVM catches this signal and in response to it starts attached listener thread and creates a Unix domain socket to communicate with gstack. Then gstack utility sends a command through this Unix domain socket, and JVM executes these commands and sends output back to the socket. The benefit of this approach is that the commands are executed by JVM itself at the maximum possible speed. But in order for this to work, JVM must be alive and healthy. And JVM also verifies that the credentials of the attaching process are the same as the credentials of the JVM process. So you cannot use this mechanism to dump a JVM launched by another user, even if you run it under root. And how gstack the chef works. It's a completely different mechanism that relies on serviceability agent. First of all, it doesn't require any cooperation from JVM. It just sends stop signal to completely suspend the JVM process. And then it uses operation system debugging facilities to read data from the memory of the remote process. And then gstack reconstructs the VM structures and walks through the reconstructed stack. A good thing is that it requires no cooperation from JVM, and it can work on a hunk or busy or otherwise not responding process. As a bonus, it can dump not only Java frames, but native frames as well. But since it requires reading from the remote process, it can be really slow. And it can work only on the same version of JVM, because it should know exactly the layout of all VM structures. Okay, that's all about stack traces. Heap dump is another essential instrument to analyze problems like memory leaks. I guess you're already familiar with JMap, the main tool to create heap dumps. Here is how a command to dump all live objects to a given file name looks like. There is a number of tools to analyze heap dumps, like Visual VM, Eclipse Memory Analyzer, and so on. I hope you're familiar with at least one of them, so I won't talk about it anymore. However, dumping heap is usually a rather slow process and can be used in production systems often. But in order to analyze some memory leaks, you not always need to dump the whole Java heap. Sometimes just plain histogram would be enough. The histogram shows you which class takes the most amount of bytes allocated in heap. GMap, like GStack, also has two modes, regular and forced. And they also use dynamic attach and serviceability agent. So the benefits and drawbacks are roughly the same. GMap without the chef asks the VM to make the heap dump, and this is really fast. But this works only on a live JVM. GMap the chef can analyze hung processes and can even analyze core dumps of dead processes. But it requires the same version of GDK, and this can be 10 to 100 times slower. So the force mode is not really good for production environments. But there is a trick to make heap dumps faster, even in forced mode in production. The trick is that you don't do a heap dump, but rather a complete core dump. Core dump is not a heap dump. You can create a dump of the whole process in operating system using GDB or gcore. But GMap can extract a heap dump from a core dump using this option. This also takes time, but this second command can be done in offline. So the idea is that the core dump is generated as fast as your hard disk can write. And then application continues to run, and then you can make a heap dump while application is already working. The same can work on Windows as well, but instead GDB, there is another tool to generate core dumps. While you can always create heap dumps manually using JMap, sometimes it is good to make a JVM dump heap automatically. The typical case is out-of-memory error. Another useful case is garbage collection, full garbage collection. For example, if you have a low latency application, then you usually don't want a full GC to ever happen because it can take several seconds. And there are JVM options to automatically generate heap dumps in such cases. By default, the heap dumps are generated in the current directory, but you can override this with a special JVM option. After an out-of-memory condition, an application is not guaranteed to work correctly. The best you can do in a production environment is to let JVM make a heap dump and restart it as soon as possible. A special JVM flex appeared in Java 8 update 92 to do this. However, these options are not really useful because it was possible even in earlier GDKs using on out-of-memory error flag. What if we decide to dump heap not only on out-of-memory error, but in some other cases? You can do it yourself. To dump heap from within application, you can use, again, hotspot private API. But a better way, and good news is that it is a standard way, which is supported not only in hotspot but in other JVMs as well, is JVM tool interface, which can iterate over heap. Using this method, you can iterate on not all classes, but if you need just to traverse some objects of some given class, for example, you want to find only strings in your application. Then you can iterate only over strings. And this is done in 2 steps. The first just tags the objects of the given class, and the second call getObjects with tags returns an array of j objects. And you can do the same for an external JVM using serviceability agent. Serviceability agent is actually a separate big topic. I don't really want to spend much time on it. Just want to show one example. Imagine that you are a hacker and you want to steal private keys from a running Tomcat server. And so you can use such program to find all private key instances in the running JVM and dump it. To use a serviceability agent, you should include SHDI jar in the class part of your application. This is almost everything I wanted to tell you today. In the conclusion, I would like to suggest to use heap dumps and thread dumps in production. And there are a number of ways to do this, both from inside a JVM and from external applications. And I will be glad to continue discussion today, anytime later. Just drop me an email, follow me on Twitter, or ask me today. Thank you. Thank you for coming.
And now it's time for questions. Some questions? Okay, if nobody doesn't have questions, so you can ask private on 6th floor. There will be a press conference. So thank you.
Hi, everybody. Hi. My name is Nikolai, and I'm here to talk about JNet 5. Before I start with that, if anybody of you have ever seen me talking about this topic before, now's a great time to leave. Because the talk will bring you through all of JNet 5, and so it's very similar to what I've talked about before. There are a few new details in there, but other than that, you would see a lot of things you already saw before, and I don't want to bore you. So, quick question. Who has been using JUnit 4 ever? Great. This month? This week? Today? Nobody. Oh, yeah, one guy. Yay. Great. Cool, because now we're going to talk about JNet 5, of course, but I'm going to need your help soon. So JNet 5 is work in progress. It's been under work for almost 2 years now. And what I'm going to present you today is a milestone, one of several milestone releases. It's the newest one. It's out in 1st of April, but it's not an April's Fool joke, I've been told. And GA release, we can hope for one in September. Nobody knows whether it will make September, but we hope it will. Which means now is still a great time to give feedback. And if you want to do that, there are several places. There's a GitHub repository, of course, where you can create an issue after you've searched for the ones that are already there, about pretty much everything that you feel should be included in JNet 5. Or if I show you something today that you think goes the wrong way, it's a great place to discuss with the team. The user guide is pretty awesome. They're active on Twitter. I blog about it on my blog. And if you want to see the slides, they're already online now. You go to slides.codefx.org, and you'll see them on the right side. It's the blue one. That said, I'm not a member of the team. I just talk about JNet 5 because I think it's an awesome project, but I don't speak for the team. Okay, these are the topics I want to talk to you about today. I want to talk about some basics that will show you how to use JNet 5, about two interesting things, dynamic and parameterized tests. Then we're going to discuss the extension model, how people can extend JNet 5. In the end, we'll come to the architecture. And then if we have time, I'll walk you through how to set it up. But that's a little bit optional. You can look that up online. So what I'm going to do now is I'm going to show you valid JNet 5 tests. And they will seem very familiar, but they're not quite the same as JNet 4. And you to tell me what the difference is. So what's the difference here? Why is that not a JNet 4 test, but a JNet 5 test? Sorry? Yeah, exactly, package scope. So the public keywords, I didn't just drop them to make the code fit on the slides. You don't need that anymore, which I think is a great little detail that was improved. What's new here? Yeah, new-ish, right? So we had before class and before. Now it's before each and before all. But they do the same. The lifecycle methods work exactly the same as before. The annotations just changed their names a little bit. I like these better because they're less technical. What's new here? Exactly, it was ignore. I thought it was ignored. I never used that, or I didn't use it very often, so I thought it was ignored, but it was ignore. Now it's disabled, so that's just a small difference. Oh, that's not so great. There we go. What's new here? So who thinks this is part of the public API? Who think it should be? A couple, great. So this is not, unfortunately, part of the official JNet 5 API, but we can make it so. We can extend JNet 5 in a way that it ends up looking like this. This is awesome because it's seamless. It looks exactly the same way that the native JNet 5 things look. And we'll see that later when we talk about the extension model. A couple of small things changed around assertions. I think most people use maybe Hemcrest or SRJ or Google Truth as an assertion framework, so I don't see a lot of reason to go through all the small changes. This is one of the more interesting ones, particularly because you can use it with these other assertion libraries as well. So what's new here? Yeah, so the assert all is new, and it will check everything. That's interesting, because before you have the problem if you have a couple of properties and you want to make sure each one is checked. All of these assertion libraries give you a way to write a custom checker just for that class, which nobody ever does. Usually you just have the three asserts there, and when the first one fails, you always ask, like, what would have been the other two ones? Now you know. You can do this. Use lambda expressions to defer the execution until assert all actually executes all of them one by one, and then tells you that in this case, all three of them are false, which looks like this. So it now tells you that what was expected and what it got on all three of those. That's, I think, great improvement. What's new here? That's so easy, come on. Nested, yeah. Did anybody ever do this before? Not with nested, of course, the notation is new, but did anybody ever organize tests in nested classes? Okay, in JUnit 4 there was a runner for that. I think it was even called nested, I'm not sure anymore. I do that occasionally. There's a great example coming up for how you could do this, but you can already see it here. The idea is that I have a class that tests some counter, apparently, and I can have lifecycle methods here, and then I can have an inner class, which is the tests are also run. I can have new lifecycle methods here, and the interesting part is that they're executed outside in. So I can slowly build the state that I want to test. I can have the counter assigned here, and then this before each method, I would maybe set it to a value, and then here I would set it to a much greater value than I have my test there. So you can organize them in inner classes. Okay, this display name is new here. So if you're going to go through all the work to basically repeat part of your name in there, then you can make your names really expressive. Every tool that looks onto JUnit 5 from the outside will think this is what the test was called. When you combine nested and display name, you have to put in a lot of effort. Well, not a lot maybe, but you have to put in some effort, but you can get really great results. So if you want to use display name to show a nice name together with nested, you can do something like this. This is the output from IntelliJ. This is an example that comes from the user guide. And you can see here that the class used to be called a stack, apparently, and then there was an inner class called when new, and then you can see a stack when new, after pushing an element, it is no longer empty. If you're going to go through the effort to write your tests like this, then you will be rewarded. If this test fails, you know what went wrong. There's not even a reason to look at the code anymore. You know what should have happened. What's new here? Yeah, the parameter is new. So I called in my server to make perfectly obvious that this is a class that I implemented. So this, of course, raises the question, how would JUnit know where it comes from? And we'll see that later, but it's a new thing, a new concept to have parameters and test methods. And that was already the basics. You can see that a lot of the knowledge that you have from JUnit 4 works very well in JUnit 5. On the surface, writing simple tests, you already know 90% of what there is to know. You used to know 90%, now you know 100%. So lifecycle methods, the tests and before and after work exactly as before, just have different names. A lot of small details were improved. And nested and display name make a nice couple if you want to use that. And we've seen parameter injection. And that's all nice, but the talk is called, or subtitle is called Next Generation Testing. And this is hardly next generation testing, right? So I still owe you a little bit. That was the basics. Do you have any questions about the basics? Anything that was not clear? Now would be a good time to ask. You can, of course, ask later as well, but if you have a question about what we just talked about, now would be a great time to ask that. Will JUnit support? Will JUnit support old annotations? The short answer is no. The long answer is it will still work, and we'll come to that when we talk about the architecture. How do you test for exceptions? The old JUnit 4 used to have the expected and the timeout as parameters behind the test annotation. The team didn't like that decision in retrospect because it kind of like overloaded the test annotation. Also, it was not a nice way to do it, right? Because you never knew which exact method threw the exception. So you can have a test pass for the wrong reason. This is assertion now. You can have assert throws, and then you give a lambda expression, and then assert throws executes that lambda expression, which is likely the method call you want to test. And then you get the exception back, and then you can assert the exception. And the same is true for assert timeout. You can say assert timeout, do this thing, and then assert timeout does this thing and measures how long it takes, and either preemptively aborts the execution with an executor service in the future, or it measures the time and then says then it didn't pass. Yes? Will before method work without static? So before each and before all and after all are run at the very beginning and the very end of that test class. And they had to be static in the past. I think actually in milestone 4, they don't have to be anymore. Or maybe that's a change that will only show up in milestone 5, but the code is already merged. So the JUnit 5 snapshots, you already don't have to do that anymore. Let me go into dynamic test. This is the short version of this chapter. I will disappoint you in the end and to show you where to read up the rest, but it's still an interesting concept that JUnit 5 brings to the table. So before JUnit 5, in JUnit 3 and 4, and even what I just showed you, you had to define your tests at compile time, right? So you wrote a test method, and that was a test then. So why would that be a bad thing? But as a default, it's a great default. It works fine. But there are cases where it doesn't work anymore. For example, if you want to create tests for a couple of parameters, ideally you want to have one test case per parameter. But at compile time, you might not know whether you have 5 or 10 parameters. Or you might actually know that it's 5 parameters, but they're somewhere in a list. So the compiler can't help you to tell you, like, you need to implement 5 methods. So if you want to move to a place where you have one method becoming 5 tests, you need to have a possibility, or JUnit needs to have a possibility to create and register tests at runtime. The same is true, for example, if you want to have non-source files, maybe some simple domain-specific language that was developed for your product where a Q&A team could write tests, or if you want to use lambdas. Some people want to have lambdas to create tests because it's the new shiny thing. Anyway, in all of these cases, you would have to create tests at runtime. And this is what dynamic tests allow. So dynamic tests are a pretty simple concept, actually. So a test is wrapped into something which is called a dynamic test. It's a class. This class has just a name, the name of the test. Also, it's at 2 fields. One of the fields is the name of the test, and the other field is something like a runnable that can execute. And then you can annotate your methods instead of with test. You annotate a method with test factory, and it just creates a couple of dynamic tests. I used to do a long chapter on how you can use that, but for the most important use case, parameterized test is actually a better approach. But it's still interesting to look at this because of the effects. Because these are fully fledged tests. If you do this, then every tool that looks onto these tests will see them as separate tests, and the IDE will show them as like that. For example, IDEs or build tools. And they're integrated into the full life cycle. This is not specifically true for dynamic tests, but for the other ones I'm going to show you. And if you want to know more about dynamic tests, there's a link down there that I can recommend you read. Because that was our dynamic test. Let's now do parameterized tests, which is a pain point in JUnit 4, and where the team worked a lot to make progress in JUnit 5, and which also makes use of this concept, of this idea that at runtime, JUnit will register tests that were not present in the source code. There are different ways to do parameterized tests. There are in JUnit 4, there are theories, for example, which has a special way of working, and there are other ways. The most dominant use case is this one. I have one test method, and I know I want to test it with 5 different inputs. And I want to run the test method, of course, once per input. And for this specific use case, JUnit 5 has native support. We'll see later which other options might exist. I will say something about that. So this is pretty easy, actually. You create the test method, and you don't say test, you say parameterized test. And then you need to define where the values are coming from. And here use the value source and say, look, the strings are hello and JUnit. And then it happens what seems natural at this point. The method gets called twice, once with hello, once with JUnit. And if I execute this with the current version of IntelliJ, I get this output. So I get test with value source, which is a method. It shows up as a node, which is in this graph. It shows not a leaf. It has nodes below it. And these nodes are 1 and 2, because I ran it twice, with the values hello and JUnit. And if I don't like these names, I can do some stuff and define the names I want to use there. But this is the basic case, which I think is really simple to use. But value source might not be the best or the only way to do that. So there are a couple of different sources. This is where you can really use, you can imagine what kinds of inputs you have and how you can put them in there, what's the best one. So value source is the one I showed you. It's really simple, but it only works for single arguments. And you need to have something else if you have like a couple of arguments that you want to pass in. Another source is enum source, where you can just say, take this enum, and then every value of that enum will be put into that method once. You have a method source. Method source says, execute that method over there, which will generate a couple of values, and use those as arguments for this method. And maybe the most interesting ones are the two at the bottom, CSV source and CSV file source. With CSV source, you can kind of write something like, which looks like a comma-separated value string, and the JUnit will do this, like split it at commas and generate values out of that and pass it on. We'll look at that soon. And you can do the same by loading from files. And the interesting thing is you can mix and match this. So for example, you have a test case where all the good cases are in some CSV file that someone created for you. And then somebody comes up with, I have a problem there, I found this other use case which we have to test. You can just add the value source then, for example, or whatever other that seems applicable, or maybe you have two different files or whatever. So you can use many of these sources at the same time. So, for example, to do this with an enum, you do this. You say enum source, and this is the enum, and then gets passed in there. You can also say I only want specific enums, specific values, and you have to name them and give them the string representation here, and then it gets only called twice for nanoseconds and microseconds. The method source, as I said, is also pretty easy. You just say this is the name of the method. I think this is going to change in the next milestone. I think in the source code it's already not names anymore, but a different name. Anyway, so you say this is the name of the method I want to call. So then JUnit calls this method, and then this one returns a stream of strings, and then the strings get passed in there one by one. Now, what do I do if I have more than one argument? This is where this class, this interface comes in. It's called arguments. And the idea is that you have one arguments instance for each run you want to have. So if I want to have one run with hello and 5, and one run with JUnit 5 and 7, like this, then I create two arguments instances. So this way I can create values and then pass them in one by one. This is where things get interesting, because this might be a very succinct way to define the data you want to place in there. You can use the CSV source, and then you just write out the things. So you can see that there's one string for each invocation that I want to have. In this case, I would have 1, 2, 3 invocations of this method, and this string would be 0, 0, and 0, and then this string would be 0, 1, and the 1, and then 1, 1, and 1.4. So each of these strings provides all the arguments for one execution, and then JUnit splits them and does things, because this is interesting, but this is just strings and doubles. This seems simple. How do they get converted? So as I said, for zeros and other numerical values, it's obvious that JUnit can just do that, right? And it does that for a couple of simple data types like primitives, for all enums, and for the things that are in java.time, like duration and instance. Everything more complex is, of course, up to you to provide. How would JUnit know to create, I don't know, in this case, a point here? And you can do that. You have to implement this thing. You have to implement a converter, which is a very simple thing. You just pass, and basically it just receives strings and churns out the data you want to use here. Sorry, the type you want to use here. So in this case, you can actually, the critical difference is here. I don't accept the point as a string anymore. I want to have it as a point. So when you want to run tests with something which like value-based types or things that look like value types, which are like point, very easily representable as a string, then this works fine. Of course, you have a complex business model. This is unlikely to work like this. But then you've seen the method source that you can use to generate actual objects. And all the same things that I just told you about CSV files, CSV source, also applies to the CSV file source. We just point it to a file, and then the same thing apply. Like this file has to be comma-separated list, so you have one line per call, and then you have within those arguments, JUnit will split them, will convert them, and will ask the converters you apply here in case that it can use the string to create whatever you have here. And the interesting part is you can generate your own sources. So if you if you have some specific feature in your maybe in your library or in your business logic that would make it interesting to create a general specific way to create objects for your tests, then you can just do that. You can just implement this arguments provider interface, which is again very simple. You get some parameter here that we're not going to look at, but you just say like, look, give me a stream of arguments back. So you just do that. In this case, I create 3 random integers between 1 and 10 and just return them here this way. So it's the first thing I do. I just implement this interface and I'm done. And the second thing is I apply it here with argument source, giving it the class that I just implemented. And now with these 2 simple steps, I implemented my own source for tests. So now I can parameterize my methods with these concrete instances. Great, so as a summary about parameterized tests, we have seen that it's really easy to declare a test method. To declare a parameterized test method with an annotation of the same name. And then on top of that, you have to apply sources. You have a couple for your choosing, which I think these one are the most interesting ones, but you can also create them yourselves. And this is the interesting part. Interesting sentence maybe on this most interesting sentence on the slide. So this was one variant of parameterized tests. If you think about something like theories, which I think have a very small use case, but they do have a use case which is very valuable, then doing theories with this would be a little bit tougher. So the extension model would allow you to you or somebody else who works on a testing library to provide other ways to parameterize tests, which don't look like this at all. They wouldn't use the same annotations. They wouldn't use the same mechanics. You could come up with whatever you want, basically, and then via the extension model, make that work within JUnit. We're going to look at the extension model next, but not how to create parameterized tests because that's a little more complicated. But again, it's really nice, but it's hardly next generation testing. It's a nice thing that JUnit 5 finally has good support for that. Do you have questions about parameterized tests? So the question is how does CSV source handle system delimiters? It uses a library whose name I have forgotten, uni something parsers, and you can pass in some delimiters and other things in there. So I guess those things are accounted for, but I don't know about the details. Other questions? That's good. So the question was about JSON. There is no JSON source. That would be a great extension to write. Or you just create an issue. Since they did include CSV, JSON is not impossible, I think. Okay, let's plow on then. Let's look at extensions. Let's look at how we can make JUnit fit our personal use case better. So JUnit 5 has a core concept, which is prefer extension points over features. Many of the features that I've showed you so far are actually implemented via extension points, which means that JUnit 5 uses an API to implement that feature that is also available to you, which means that these extension APIs already, I wouldn't say battle tested, but let's say skirmish tested. So it has already some use cases. So JUnit 5 actually has literal extension points. And what is an extension point? These are extension points. So we're not going to go through all of them, but you can see some things here. Like you can see, for example, the lifecycle methods before all and before each. There seem to be some callback thing. Parameter resolution corresponds to the fact that methods can have parameters. Then you have exception handling here, for example, which makes sense because, of course, a method can throw an exception. So maybe you want to interact with that. You see, these are different extension points. In the end, an extension point is just an interface. And most of these interfaces are really simple. So you have one interface for each extension point. And usually JUnit captures all context, so all the interesting context that is currently going on at that point in the test execution, gathers that into an instance of test extension content or container extension content, but you get one of these extension context and you get them passed into your method. When you remember back at when I talked about creating your own sources, there was the brackets with had 3 dots in there. I said I wasn't going to talk about that argument there. It was one of these. So Jane would capture the context, pass it into your extension, and then you just do whatever you think works best for you for that extension. And of course, you will implement several extension points usually to interact with several. So have your extension interact at several points in the test lifecycle with JNet. So let's do some simple extensions to see how this works. So the first thing is you want to benchmark our tests. And if you write that like this, we say for each test method, we want to write the elapsed time to the console. This is more like a business language, like regular language. We can write more technical. We can say before the test execution, store the launch time. After test execution, print the elapsed time. And this is almost as precise as the code. So you will see that before and after test execution, there are extension points before test execution callback and after test execution callback. And we simply implement both of them, declare a field here, and then override the 2 methods that belong to the interfaces. And you do exactly what we just described. Before the test execution, I take the current time millis and assign it to system. I'm a fan of static imports, so this would be a static import. After test execution, you just do current time millis, subtract the launch time, and then you format the thing, and then you print it out. So this would be a very simple extension that just runs before and after each test execution, stores the time in between. So remember, disabled on Friday. Let's see how that worked. There is a test execution condition. That's an extension point. That interface has one method. The method is evaluate, and it returns an evaluation result. So the idea is you return an enabled result when the test is supposed to be enabled and a disabled result when it's supposed to be disabled. These are the corresponding static factory methods on that class. And here we also get this context, but we don't need it. Like before, we're just going to ignore it because all we do, we check whether it's Friday. And however you want to implement that, you check whether it's Friday. And if yes, you just disable the test. And there you go. There you have the extension that we talked about. Last one, I promise. Parameter injection. How does my server get here? This used to be the most complicated extension point. Now the way to customize parameterized tests is considerably more complicated than that. But it tells you about generally how simple these extension points are, because this is most complicated because it actually has 2 methods. So what you do here, first, JNet is going to ask your extension. Look, this is the context of the invocation. Specifically, this is the parameter I found. Are you in charge? Do you support this one? Yes or no? If you say yes, then you will be asked later to resolve the parameter. If you say no, then you won't. If several extensions say yes, then JNet quits and says, several extensions said they were going to support this. I don't know which one to call. Fix this. So in this case, I resolve the parameter here and just return a new my server. This example works based on the idea that I have this class and I know I want to create this class. But you can think about other extensions. Maybe, for example, you have an extension that mocks objects. Of course, mocking is possible for all kind of objects, right? For all types. So the mocking library would always say yes here, and then would sometimes lead to conflicts. So it would be a different way to do that. Different way would be you annotate the parameter. The extension would only be activated, would only say I support this type or this parameter if the parameter is annotated with, for example, at mock. You can ask the parameter context and say, what are the annotations, or you can even ask what are the annotations on the class, or you can, from this context, you can explore via reflection the whole surrounding of the test. And you can come up with whatever kind of rule you want to decide here whether you support a specific a parameter, and you can do the same stuff here to create that parameter. So how do we apply extensions? So far, we've just created extensions. How does JNet 5 know about them? This mechanism is really simple. You just apply this annotation extend with something, whatever your class is, and then you apply it to either a test class or a test method in there. And that's very nice. It works, but it's really technical. It doesn't look so beautiful. Remember that at disabled on Friday, that looked much better than this. So this is the way that works. Now we're going to look at the step that makes it more seamless. This is my experiment to see how often I can write annotation on the same slide. Who knows about meta annotations? Okay, meta annotations are actually nothing complicated. It's just something a little bit unusual. If you ever written your own annotation, you might have added another annotation on top of it, like retention policy or target. That was a meta annotation. A meta annotation is nothing else but an annotation on an annotation. This is a Java feature. What JUnit 5 does, it is aware of this feature and looks for meta annotations. So whenever JUnit looks, for example, on a method and it sees 3 annotations, it doesn't stop there. It then looks for more annotations until it explored the whole tree of meta annotations, and then it acts as if all of them were present immediately on the test method. So this means you can apply annotations without having them directly present. You can make it once removed or twice removed by putting them on other annotations. So we can create our own and use them within JUnit. So the one above is the simplest one. I did not put in the retention policy and the target here, but this is the essence. You create this is the way to create an annotation. You create a new disabled on Friday annotation and just extend it with your own extension. And you can do the same thing, for example, for integration tests. Let's say for integration tests, you want to say integration test is, of course, a test. I want to tag it. You can use tags to filter test, which we're not going to look at here. And then I extend it with benchmark extension because, you always want to know how long integration tests run. And because I want to most likely test my parameter, I put this resolver in here as well. And then I created a new annotation integration test. And now when a test method like this occurs, then JUnit 5 comes along, picks integration tests, and resolves all these. Sees disabled on Friday and restores all these, and then explores all these. So in the end, it's like as if test login had these 5 annotations on there, which means JUnit 5 knows it's a test. It knows it has 1, 2, 3 extensions, and it's tagged. So this is the way to integrate our own extensions into JUnit. So the summary of the extension model, it's very flexible. You have a lot of different ways to interact with JUnit. It's not complete yet. There are things you can't do yet. For example, there's no extension point to push the execution of a test onto different threads. So if you've ever tested UI, then you know that you have to do it in a Swing event dispatch thread or in the JavaFX application thread. So for JUnit 4, they used to exist rules which would basically take the test that you want to execute and execute it in that thread. For that kind of extension that interacts with threading, there is no support yet. I hope there will be before the GA release, or otherwise at any time after that. Extensions seem to compose well. It's always hard to tell until there's a gigantic ecosystem of, like with JUnit 4, like with rules. It will take a while to find out whether they really interact perfectly or whether they do stomp on each other's feet. But they were designed in a way that would make it at least less liable, reduce the chance of that happening. And because of the meta annotations, it's really nice to customize those. So again, where's the next generation of testing? Again, we're still talking about JUnit 5 being great to use in your project, but that doesn't answer the question of what that has to do with the rest of the JVM. Second to last point, architecture. Oh, before I go to that though, questions about extensions? Yes? So is it possible to set the sequence of tests? This goes into the direction of like what testng does, I guess. The testng has one test instance, and then you can define it in an order in which the test methods are executed. For example, so you can slowly, let's say, I log into the web service, then fill the card, then check out the card. This is what, in JUnit 5, these are called scenario tests, and this is what the current milestone will hopefully eventually deliver. If not, the team thought about maybe doing first a 5.0 release and then do scenario tests after. But there is no support yet because they will not intermingle this other way of doing tests with the more normal unit tests. So they want to make sure that there's a separate API for that looks differently. Like says most likely scenario test and then explicitly links to how tests and which order tests are executed. And I hope that then there will also be an extension point for that. But that is not the case now. Yes? There would be the question whether there would be new test suite API instead of the existing one. Yes, JUnit 5 is a total rewrite, and while concepts that JUnit 4 used might still end up in JUnit 5, I would not think that test suite is one of them. And even if it would end up, it would just be the concept, not the same code. More questions? Okay, then now architecture. If you wonder now, like, why would I care about JUnit 5's architecture? Wait, in the end, I guess you will care. So if we talk about JUnit 4, then the word architecture, if you talk at an artifact level, then it hardly deserves the term architecture, because it's really just JUnit 4 and then there's a little Hemcrest on the side. But other than that, everything is in one jar. So when you write tests, you use that jar. When you write an extension, you use that jar. When you are a tool and you want to execute tests, you use that jar. And the whole mechanics of executing and finding tests, or the other way around, they're all in there as well. So there's no separation of concerns at all. And this is not just an academic complaint, it actually has consequences. Because the tools that we use, IDEs particularly, give us a lot of nice features, but the API was often not powerful enough. So what do you do when you use a library and it has the thing you need, but it doesn't expose it? Somebody laughs. Reflection, right? So sure, that's what happened. Tools started to use reflection to go into JUnit 4 and take out the values they needed. And this was a problem because it bound tools to implementation details. And this made maintenance very hard. Imagining working on a project where you can't change some field names because then some downstream tool will break. This is not a great way to maintain a library. And this was apart from this other one was the extension model in JUnit 4, which was not that great. It worked fine, but could be improved. That was one big reason. And the architecture was the second big reason why JUnit 5 is a rewrite and it's not just JUnit 4.13. So JUnit 4 was kind of like ended up in a dead end. And Johannes Link, who was one of the initiators of the new project, once put it like this: the success of JUnit as a platform where everybody writes tests against and other extensions and even other test frameworks integrate with, that success prevents the development of JUnit as a tool that we just want to use to write tests. And they want to develop a JUnit 5 that doesn't have that weakness. So the idea was to separate concerns, to have an API to write tests against, and then you have an API on the bottom and you have an API for tools to run tests. That makes sense to separate those. And then in the middle, like kind of sandwiched, you have a mechanism that gets told do something and then looks at the tests and builds the whole thing. Or what I just told you, like look at what is annotated with a test and check the extensions and all of that. This was the original plan. And then when they looked at the second point a little longer, they realized that there's another split they can do. So first and third are the same. You have an API to write tests against. At the bottom, you have an API for tools to run tests. But in the middle, another layer of abstraction was introduced. So for each specific kind of test you want to write, you get one engine. And then something orchestrates engines. And in between that, you, of course, need an API. This is a critical difference in thinking what JUnit 5 does, because that splits JUnit 5 in a lot of submodules and subprojects. Like, I don't know the number at the moment, but it could be somewhere at least a dozen, maybe more, towards 20 jars that make up JUnit 5. And this also means that there are a couple of new names. One of the three subprojects is called JUnit Jupyter. Whatever I told you about so far, the API, the extension model, all of that is part of Jupyter. So if I would have been precise from the beginning, I would have always said this is JUnit Jupyter stuff. Then you have JUnit Vintage, which operates on JUnit 4, but integrates JUnit 4 into this mechanism. And then you have the platform, which is a totally new concept. The platform is meant as an integration point for tools, specifically IDEs. So they would never again have to talk directly to these artifacts up here. They will always only go to the platform and tell it, here, run these tests in this package, for example, or run this method. And then the engines and the whole thing do the rest. So this is what it looks like with JUnit 5 in the game. You have all the tools down here. You have to run the platform runner here, It interacts with this JUnit platform engine, which is an API module or jar. It contains nothing or few things besides some interfaces. At the top, you have your tests, which are implemented against the JUnit Jupyter API, which is a small artifact, also mostly annotations. And then you have the Jupyter engine in between. It implements this engine interface, and it operates on the JUnit API. On the Jupyter API. So to summarize, you have a clear separation of concerns in the API for developers and tools, but how is this next generation testing? This is the thing. This is the reason why the talk is not just JUnit 5 is nice for JUnit users, but why I think it's a huge difference, because it opens up the platform. So if you want to say you want to have JUnit 4 tests to run within this architecture, all you need is create an engine, which you shouldn't do because there is one, but the concept. If you want TestNG to have the exact same support like JUnit, you only would need an engine. Whatever else you can come up with, you only need to implement an engine. And as soon as you do that, as soon as you implement an engine, you can integrate it into this process. So the tools down here, again, they only use the same runner as before. You just plug whatever you use here, whatever, this is made up, right? So TestNG is not made up, but there's no integration to JUnit 5. So whatever you think you could write tests against, all you need is this artifact that implements this interface to make your testing framework of choice work within JUnit 5. And I think this is an awesome development, because once tools natively support JUnit 5, first of all, the tools themselves have most likely less maintenance effort into supporting different testing frameworks. They could theoretically say, we're not supporting JUnit 4 specifically anymore, we're just supporting the whole new JUnit 5 platform thingy. So they could drop support for other frameworks. But at the same time, these other frameworks would have most likely better support than today. As soon as they implement an engine, they get like 95% of the tool support that JUnit has now. And this means that developers can try out many more things, because now if you have an idea for a testing framework, it's kind of like it's a chicken-egg problem. Nobody's using a framework yet, of course, but it's hard to make them use it if there is no tool support, and to implement all the things you need for Maven and Gradle and various IDEs is a lot of work that you just, if you have a weekend project, you're not going to master. At the same time, on the other side, if you want to try out a new testing framework, you're in the same situation. It's hard to convince somebody in your team to use this new testing framework if there's zero tool support. And without using it, you will never, ever be in a position to, or most likely not be in the position to give back to the project and support that project. So now you can. Now all the maintainer has to do is create an engine, a JUnit platform engine for his specific or her specific testing framework. And I think this could give rise to a new generation of test frameworks, which much easier to be creative, come up with new ideas, and at the same time try new things out and give good feedback and find out where the new approaches are valuable. So because the success of JUnit as a platform, that was once the thing that inhibited JUnit 4's development, because this becomes available to everybody, I think this could herald a new generation of testing on the JVM. There could really be, hopefully there will be many tools over the next years, new approaches to testing that you will be able to try out if you want to. JUnit 5, I think JUnit 5 is pretty nice, but it's still interesting to see what people can come up with. And they already do. There are a couple of different test engines already, which basically mostly they do this the spec thingy that also works. I think Kotlin does it as well. Where you can write tests in a specification kind of way. You can look up those links. And other projects already started. I want to name this one specifically because I began it, where people already start to interact with the extension model for Jupyter. So this would be a different engine, and this would be projects that mostly interact with Jupyter's extension model to provide new features for it. And the JUnit team has a list with projects somewhere that you can look at. So the real summary of the architecture is, as I said before, separation of concerns, but these are the important parts. It opens up the platform, and it might lead to tool support for basically every testing framework that people can come up with. And talking about architecture, there's even a little bit more to the story. Do you have questions about that? Are you now convinced that this is the next generation of testing? Is it production ready? JUnit 5 production ready? No, it's not. We can have a look at the setup slides in a minute. First of all, there was not even a general availability release. And as I said, we expect one in September, so let's say sometime in fall. And then full support in tools will likely take a moment longer. IntelliJ is really good at the moment already. You already get nice tips when you do something wrong with parameterized tests, for example. We'll complain that there is no source. So they are definitely on the bleeding edge of this. Eclipse integration is lagging a little bit, but, we just look at those slides then, right? This is for the tool. So IntelliJ, you can already use it since this version. If you want to use Milestone 4, you have to use this version, though. With Eclipse, you get early access support if you install some milestone of the upcoming 4.7 release and then do some shenanigans. It's linked in this issue. I didn't find anything for NetBeans. And Maven and Gradle, there is support developed by the JUnit team. So as a proof of concept and to get people started, they implemented a Maven Surefire provider and a Gradle plugin that does the basics. And they handed them over to the teams. So the Maven team got the source code and will most likely use that to start on a Surefire integration. And apparently Gradle wants to revamp their test, how they approach testing, how testing works within Gradle. So that might take a while longer. But you can already use the plugins that are there. And you can see the user guide for how that works. Let me go to the beginning of this just to say one last thing, one important detail. So if you want to use tests, you just do this. If you want to write tests, you just need this one artifact. This is you now recognize everything you need to know. You'll see the Jupyter here because it's just the Jupyter API you want to use. And just this one jar. As I said, support is still work in progress, but IntelliJ already works quite well. Build tools, I also just told you how to use in the build tools. If none of this works, if you want to if you're stuck on an old version of IntelliJ maybe or NetBeans or something, what always works is kind of like backwards. So we've just seen how JUnit 4 could be run as part of JUnit 5. You can do the same thing the other way around. This here is a class which will contain JUnit 5 tests, but you use this JUnit 4 annotation. So, and then you use a tool which runs JUnit 4 tests. It will see this as a JUnit 4 test class, instantiate this runner, and then tell it to run this thing. And this runner knows how to run JUnit 5 tests. And if you don't want to do that for every class, you can do it like this. You can have one class that you just put anywhere in your code, in your test tree. It doesn't matter where. And then just say select a couple of packages. And then with this selects all packages that are below that as well, right? So it interprets them as hierarchical. So this way you can have one test class and have all of them run as part of JUnit 4. So if nothing of the other steps work for you, this does. There's a console launcher. I'm not going to go into that. You can run from the console. It has nice, colorful output. It's pretty good. It's the most up-to-date launcher at all times because it's developed by the same team. So you can start writing tests right away. Only IntelliJ has native support so far. Other IDEs are catching up. And there's provisional Maven and Gradle support. That is working fine. It works fine for demo projects. I'm sure if you have a big project, you might have specific needs that they don't fulfill yet. But I hope that by the end of the year, support will be much better than that. And if you run with JUnit 4, it's a good compromise. If you have older tools, that works. Final summary slide. You've seen the new API, which is like an incremental evolution of what you know before. You've seen dynamic tests, which I didn't show you why, but which can be pretty useful. But you mainly focus on parameterized tests, which show a nice way to create tests for different parameters. Look at the extension model, which I think is very promising. And the main thing why I like JUnit so much is the architecture, which really opens up the platform and gives other testing frameworks a chance to integrate with it. And tool support is not quite there yet. That was that. Thank you. Usually I plug my book, but with the recent decision for JSR 376, I would hold off on buying. Who knows whether it should at some point be called the Java 10 module system? I don't know. We'll find out, I guess. If you want to know more about that, I recently wrote a newsletter. I have a pinned tweet you can find here where I talk about module system of the upcoming thing. Otherwise, you find me on my blog here, and I write a newsletter here, and Google Plus, and blah, blah, blah. If you have any questions, you can ask them now, or if you see me run around the conference or in the city, whenever. So, more questions? Yes? Test coverage, the question about test coverage statistics. I think the team tried to use Jacoco on their own code base and didn't work out that well. So I'm not sure whether that's already a working thing or just a thing that needs to work at some point. Okay, if there are no more questions now, I'm gonna let you go. Oh yeah, one more. Can you mix JUnit 4 and JUnit 5 tests in one project? Yeah, you've seen the slide, remember, where you had the three things side by side? So you can use that mechanism to do that. So yeah, that's not a problem. Actually, that would be my recommended approach. There's no reason to move JUnit 4 tests to JUnit 5. That would be a lot of effort for no real benefit. I recommend you can start writing JUnit 5 tests like right now, and maybe sometimes you have to use an extension, a runner or rule, which you don't have a JUnit 5 variant of yet, then even write new tests in JUnit 4, it doesn't matter. You can basically mix and match them in the same code base. And with this architecture of two different runners, each runner will only execute the test that he's in charge of. Yes? Why is it not production ready? Well, it works fine. But first of all, tool support is not quite there yet. And then second of all, there could be breaking changes. They are unlikely, but it has not been officially released. So breaking changes would mean rewriting tests, and nobody wants to do that. I'm out of time. Thank you very much. Goodbye.
Hello? Okay, thanks for coming, and I changed a little bit my title's talk because people were expecting me to give tutorials on how to use some particular libraries. So I think it's a little bit about that, but not exactly. Today I'm going to talk, half of the talk is about how to design things, and half of it is about what to expect from mocking libraries. So that's the idea. And before we go into this, I want to learn a little bit about you. How many of you are Java developers? Cool, so everything will be easy to understand for you. I even will speak a little bit about Ruby, so don't worry. Okay, so first of all, why I do this talk? Because, you know, I tried testing, manual testing, I didn't like it. Then I said, like, what can I do about it? So I started to write unit tests. And then I found out about mocking. And, you know, mocking, who likes mocking, by the way? Okay, so you're lucky. I hate mocking. And that's why I'm giving this talk, because I think I hate mocking because I had so much time that I spend debugging my test because of mocking. And I really want to share some experience with you for the things that I didn't know before. And so I will talk about frustration. I will maybe cover a little bit. Mocking is bad. Like, this is like that motivation that people say, okay, mocking is bad. And mocking is bad because, you know, I get frustrated. Many of you get frustrated. And maybe some of you like mocking and then abuse it. So I don't think that mocking is particularly bad, but maybe it exposes some design issues. But let's see. And wasting time debugging tests. The whole premise with test-driven development, for example, is that you should get instant feedback, and that feedback should stop you from learning how to use debugger. That's, for example, what Uncle Bob says. And another thing that I really want you to take away home, don't use libraries, tools, frameworks religiously. For example, if I'm front-end developer, there are other tools than Angular or React or something. Just learn our things. Try to understand what's going on with them. If you're a Java developer, who will use Spring for their applications? Come on, most of you. But do you know any other alternatives for Spring? That's great if you know, but if you don't, this is your homework after this talk. Sorry? Yeah, that's a troll in the audience. Great. Okay, so I'm not saying that those tools are bad, but you need to understand what to expect from the tools, and you have to challenge those tools. Don't let tools challenge you. Okay, so, and for example, if I mentioned Ruby, I will mention it again. If we speak to typical Ruby developer, they will do everything with Rails. I think we shouldn't end up in such situation. We should question what we do. So, agenda for today is why do we care about mocks? This is more about like theory part in this talk. Then the most important one, I will show some examples with Mockito, JMock, and which also apply to our JVM libraries. And what I really want you to remember is the content of that second part, because I think most of you don't know this. I also didn't know it for maybe 8 years of using mock libraries, and then what I did, I just finally tried different tools, different languages, and I realized that how stupid I was. So this is about that, and I hope you will learn something new. And I did one thing, like in the end, like that frustration with libraries led me to a situation that I said, okay, probably I can do it better. And it turned out that probably it's not the case. So what I did, I wrote a small, simple exercise at home during Christmas time, and I wrote my own mocking library. And I will speak a little bit what are the challenges writing mocking library, and basically what are you trying to solve by doing that. So it's like getting into the boots of a mocking library developer. A little bit about me. I organize Vilnius Java user group, but I don't do Scala for more than 3 years, which is like a shame. I still like Java a lot, and I think like it's especially the platform. I can do full stack, which means that you just need to know JavaScript and CSS. That's what it is. I'm a huge TDD enthusiast, and mostly care about software design. That's why I do this talk. And I have this slide because I want followers on Twitter, where I mainly tweet something that I hate or just like random quotes that I come up myself. So you can reshare or something. So let's talk about testable design. And why do we care about it? So as I told, I hate testing. So I decided to automate. And to automate stuff, it's not so easy after all, especially if you write tests after you have production code working. And testable means that you can split your system into components and verify if they work correctly. Design means that you are able to change that software in the future easily. And putting those things together is a valuable thing. And if you want to dig more into this thing, I really recommend to start maybe with this book. And it's like a challenge for you, because I had to overcome this myself. To read Ruby book by being Java developer, it's like a mental shift. So go out of your comfort zone. By the way, who of you know what Sandy Metz is? So go home and watch her videos. She is very good on software design. I think Yegor mentioned null object pattern. She has a talks on that. So go and watch it. Like she's more on design than Ruby, and it's a good book to escape your comfort zone from being only Java developer. And today we're full stack developers, so knowing our languages like JavaScript, it's a good thing, and I think this is like a good compromise to learn about design. And it's not only about object-oriented. It's more about design with some examples in Ruby. And what's nice about it, that Ruby is not static language. So not being dynamic language brings some challenges, and you can see how those challenges can be solved by designing software. And what is object-oriented design? I would put away object. I will just leave what is design, and it's about managing dependencies. And dependencies are something that we should care for one simple reason. If I have to add feature to one place of the code, I don't want to change my dependencies. I want to have a cohesive place to introduce a change. And this is what design tries to solve. It's not about making code beautiful. Beautiful is something maybe what pleases me, but in the end, a company product doesn't benefit from it. And as I said, purpose is just to allow you to change, add features later. And this is a wonderful quote, and I think this tackles what design is. Another great book that I recommend reading is Growing Object-Oriented Software Guided by Tests. You can delete that last part, guided by tests. It's about growing software systems. So this is how to solve many different problems that happen along the way you develop. And what they say about design is that design is about things that happen between objects and not about what's inside the object. Inside is something that is your own problem, but usually systems are composed of multiple components, and they break. And the biggest challenge is to make stability between those connections between objects. Another thing what they say about design is that interface describes if two components will fit together, which means like I have one thing and another thing. Both are objects. They have no behavior. If you can connect them, that's it. That's what interface does. And from design's perspective, what is more important is that you need to understand if those things will work together. For example, if you put tire on the car, does that tire actually fits that sports car or no? Like, can it handle the speed and so on? So this is what protocol is. So you should, when you design Java systems, you should think more about behavior than if things fit together. Okay, so let's talk about testable design. So in the middle of this picture, you see one thing where on top it's written mocks. So mocking is about mocking your own things. So this light blue area is where you develop your business logic. And you try to put everything that is not yours to the boundaries of that logic. And you guard yourself from that world which is not yours by asking to provide protocols. And for those protocols, you write your own adapters. So this way, you make one interesting thing that you don't need to know which database you use. You don't need to know which UI you use. Maybe that's like testing UI, which is like a fake JavaScript engine or something. And mocking happens inside this circle. You can also, and question is, what do you do about those parts that are outside the circle? And for those parts, well, you cannot mock those parts because something which is not yours, you never can be sure how it works. So what you can do, you can only integrate or you can end-to-end those parts. And this architecture or design is called ports and adapters. And idea behind it is that application should be equally driven by things that you don't know, like from the outside that exist. Like your application should be written so that you don't leak into your domain logic any details from the outside. For example, if you need storage, you don't care about what type of the storage it is. Maybe that's a storage which doesn't store anything. It just like sends your data to another storage, like a proxy. Or if you have a user interface, that user interface can be browser, can be test, can be something else. And this architecture also known as hexagonal architecture. And you may ask, why the heck it's called hexagonal? And I will quickly explain why. So let's say we have application. So this is where we write our business logic. For example, we can be a bank or maybe some other software company, as it was told in the morning that everyone is actually working now for software companies. And this application doesn't need to know about MySQL. And you see this hexagon lets you visually put another hexagon side by side. So this is the answer why this architecture is called hexagonal. And another interesting thing happens that MySQL is, again, another application. And for MySQL, this application looks exactly as like a known thing. It just provides some port which you implement with adapters, and that's the way you separate yourself. And going even further, like we can add JavaScript UI. By the way, those ports are usually called, they have two types, but it's not very important. One type is primary. Primary is user interfaces, and secondary are storages, queues, or whatever, emailing systems, and so on. So for JavaScript UI, we get into the similar situation. We can write single-page application. We can test it in isolation without even knowing what our backend is. And if we want to test backend, we can create acceptance test suite, which doesn't know about JavaScript UI anything. And application doesn't really care where it's like a real user interface or is it like a test that we have written. All right, and in production, we can automate some production test cases and have a smoke tests running. So this way we have like hexagons that do not know about our existence. They just communicate over protocols. If we are Java developers, those protocols can be interfaces, but they don't have to be. It can be network, it can be HTTP or something like that. And for example, the last example, backup service. It really doesn't care about this application, but what we do, we actually backing up data which was collected using this application. So this is the point of hexagonal architecture. And now it's a perfect time to start talking about mocks and show you some code. Okay, so I will speak about Mockito and JMock, and my goal is not to blame someone or say that those libraries bad or good at some points. I believe that both of those libraries are like really good and they do job if they are used correctly. So let's start with Mockito and look at simple example. So idea is that I specifically skipped additional lines so that you expect something to appear here. And what we are going to test, or what is our system under test, is sales reports, which will depend on finance. And for dependencies, we will mock those dependencies. And by the way, anyone doesn't know Mockito? Okay, so a simple idea is that you just get a static helper mock and you pass a class name and then you have a fake finance or your class instance. And then you can tell how this fake instance will act upon some situations, and we will see how to describe that later. So basically what Mockito and some other frameworks let you do is to, instead of forcing you to implement that interface separately from your test class, you can implement that class using proxy by just using nice DSL language in your test code, and sometimes abuse it. So my question is, what will happen if I run this one? Of course, you don't know what happens under the hood, but what is the most typical situation? So the most typical situation is that if I pass a mock, probably something will be called on that mock, and if you do that with Mockito, you end up with null pointer exception. And sometimes if your tests are written in the way that they are very complex, they use complex collaborators, it can be a nightmare to debug them, especially if they are not unit tests, but some integration tests that depend on many things in the system. So this is the problem that I hate the most. Like, it's a consequence of something that I don't know what. I just know that my test doesn't work. It doesn't explain what is the cause of it. So to fix this, well, we're fixing null pointer, but not fixing our test in the way that it becomes better. So what we will do, we'll just add a stub. What stub? And some people call this mock, but this is not mock. It's just like stub, which on this call with this parameter will return this value. It's not mock. I will come back quickly what mock is. And if I add additional verify statement, that stuff turns into the SPI. And SPI is something that you run the system, it finishes execution, and then you can do postmortem analysis what happened with the system. And according to that analysis, you can say that, okay, my system works or it fails. So you can feel that things happen after you run the system instead of saying what you expect to happen before you run. So this turns, and to catch null pointers, most of the time you need to look into stack traces or maybe to run debuggers to understand where the heck I lost my value and what was called. And it becomes a bit harder if you have a lot of mocks. Okay, so let's look how JMock handles this situation, and pay attention a little bit about the syntax, about how natural those frameworks look. I think Mockito looked pretty natural. Its DSL is very well understood, and it's easy to write it yourself. Again, I have something missing here, and we will add it later. So the same situation, the same finance class is dependency for sales reports, and when I run it, it says, okay, finance is not an interface. What does it mean? It means that JMock doesn't know how to make mocks out of concrete implementations, which did just work fine with Mockito. And some people think that this is a good way to go, and I think many of us, especially who are in design, we think that we should split interface from implementation, and it will definitely bring some good, potentially for the future, it will be easier to change. But I think that we have such a wonderful tools nowadays that it's much easier to factor out implementation from existing concrete implementation than to start separating interface from implementation from the beginning. And if you start doing that, there is an obvious problem. The problem is that you need to come up with two names, one for the interface and another for implementation. Of course, those people who are into design, I think they are completely right, because if you start from the beginning extracting interfaces, they have one thing in mind, which is that you change dependency from implementation into interface, which decouples your user from implementation. But sometimes you don't need this, especially if you have single implementation. You don't use any I don't know, RPC implementations or something which requires you to give away API separately from implementation. So I would say that you should decide yourself. I usually try to extract implementations later when I get a feedback that I need them. And on the other hand, from customer's point of view, if I get a class, I usually don't care, is it interface or implementation? Every implementation has public methods, and those are imaginary interfaces that I only can call. And don't forget that we care about works versus fits together. So interface only will guard you from fitting. Okay, so for JMock, there is definitely a solution. You just tell in an ugly way that you are going to allow mocking finance like concrete implementations. That's ugly, but that's a solution, and probably you can factor it out into something more beautiful, but that's not the point. And when I run this code, now I get another thing which I actually like. What it does it produces a report which says that it just received unexpected invocation, and if you have multiple of such lines, it will clearly explain what happened before and what it is going to expect. So I think this is a good plus from mocking libraries, and this is where mocking is different from spying or stubbing. Mocking sets expectations, and mocking is about expectations. And expectations, if they fail the whole test. It's not about looking into postmortem result, trying to catch some null pointer exceptions. Okay. So again, another ugly part is how to write the same expectation that we know from report that we are missing, and this is how it's done. It's an ugly old implementation. Probably some junior programmers wouldn't even know what those two braces mean here, and this is another homework for you. So it's also a bit ugly because to define one stub or mock, you need to write, in stub case, you need to write two statements and not mess around with them. Okay, so I think Mockito has very nice DSL, and JMock does mocking right, but JMock just looks a bit maybe old, I would say, or its syntax is very verbose. And it also breaks given when then style. If you look back, you see I set expectation, but I don't assert anywhere that such thing is required for my thing. So this breaks given when then because I only give and then happens exactly at the same time where I'm giving. Also, when you expect and require something to happen, you are in the risk of overspecification, and if you overspecify something, it may be a smell that your design is too complex and you should just change your design, listen to a test. And also pick one, verbose or implicit, and Mockito does many wonderful things by not telling you that it's doing that, and the same happens with JMock. And this is the problem, like we have either very verbose syntax or we have to do things implicitly. Okay, so what happened with Mockito? I created stub, I executed it, then I had to debug nulls. I needed to understand where the null pointer came from, and then I had to repeat until I make my test work. What happened with JMock? I set an expectation, I executed my system, then looked at the report that something was wrong, and according to that report, I fixed the test. Looks very similar, but one works on the actual result of the system, another works on the actual result of the test, which is very important difference. So, what is mock? Mock is an expectation set before exercising system under test. And spy is something that you look after you have exercised your system. So it's an important definition. And one more thing, you can also set expectations with Mockito. Just many people don't know about that. And because it's very hard to find out that such feature exists, nobody uses that with Mockito. And J.B. Rainsberger has a strong opinion on spying and stubbing, and he says that both of those things are actually synonyms, and they solve idea of something that I call myself of patching. So, for example, if you need something from dependency, you provide a patch and see if that works, but without really knowing whether it was a correct patch. And what community says about it? Community says one thing, again, this book that I recommend to read everyone. So one thing is tell don't ask style. Tell don't ask style says that you should send commands to objects or send messages instead of querying them for data. Well, if you do functional programming, it may not be the case. And I think authors of this book also have slightly changed their mind, but I think it at least forces you to think about some object thinking ideas. Another thing, only mock types that you own, which is the idea that you can mock or set contracts on things that you can control. If you mock stuff that you don't own, how can you be sure that your mock is correct? And don't mock values. If you need to mock values, it means that your value is too complex. Just simplify design. Another approach is lenient approach, which is promoted by Spock. And I think that lenient is equivalent to spying. So some community believes that spying is still better. I believe that strict behavior is a bit better because it quickly gives you feedback. And I think testing is about quick feedback. It's not about getting information that your system works. It's sometimes more important to understand what doesn't work and what you need to fix. It's about the time that you save by having automation test suite. Okay, so I had some time during Christmas and while visiting families and so on. So I decided to play an exercise and to write my own mocking framework. It's not for real use. It's just like you can find it on my GitHub, but it's just like an exercise. And it's good exercise like a kata. I also wanted to understand why the heck authors of those libraries did things that so much annoy me. So I tried to avoid those problems. Also wanted to understand if use of Java 8 features will improve mocking syntax. And another maybe less important thing, I wanted to find a project where I can use some code generation and learn byte body. Okay, so the idea is that I had to unlearn what I already know and start from scratch. So my goal was that API should be explicit. It shouldn't have any surprises. With JMock, with Mockito, you can quickly get into surprises because Mockito is not thread safe. It does things that you don't expect sometimes. JMock definitely very explicitly says that it depends on the order that you specify your expectations. So this is what I came up. And the idea is that you create mockery. By the way, JMock does the same thing, but if you run with JUnit, there is an integration which can hide this boilerplate that we have here. And I passed my collaborator class, which is like in previous example, it was finance. So I create mock by just passing a class and get a proxy object and then set expectation. And I have two types of expectations. One is command, and another I will show in a minute. So I wanted to have more succinct syntax, but I couldn't come with better one. So if you know something that could improve this, you can come up with a pull request and send it to me. So idea is that I pass collaborator, and then I said I want to mock a command. Command is something that doesn't return result. It just accepts a call. And that command takes lambda, and that lambda knows which methods our collaborator has. Why this syntax? This syntax is important from the IDE's perspective, because this one is very well checked by IDE and by the compiler. And then you call a method, and if you call exactly what you mocked, what you expect, it will pass. And then if needed, you can call optional verify. In case you didn't call anything, you may want to call verify. Very similar with querying. Querying is when you return value, or in Mockito case, it would be stub. And you say, okay, I want to query. I want this query. And when this query comes, I will return this. Again, this syntax is what I come up if I want to have IDE to autocorrect me. And how it works, you just call the same way as previously, and then if needed, you can verify. So this is the API. It's very simple, no hidden implicit ideas. It's still not thread safe. In theory, it's not thread safe. You can come up with some race conditions, but it's easy to fix that. And to implement a mock, I used JBuddy. And JBuddy is a very nice library. I think from usability point of view, it's probably one of the best. I still would say that docs are not the best on the market, but as long as you try to do something and find out the way how to do it, it's very obvious what's going on and easy to use compared to our libraries if you have used before. Also, Googling helps a lot. Author of the library is very active, and probably you'll get your question answered very quickly. So how does it look? So you have you call ByteBuddy, you pass a class that you want to mock. So in my case, it would be collaborator. And you tell, okay, I want to match all methods, for example, in my case. And then I say when this method is intercepted, just send information to delegate. So basically it takes all the parameters and all the call information and transfers to delegate method. And when you say get loaded, you basically create a proxy class. And then what delegate does, it has many annotations, which are, I don't know, probably they reduce boilerplate, because otherwise you will have to have a lot of parameters and then specify those parameters that you are not using. But anyway, I think this was the hardest part, that I spent my time on trying to understand which parameter works in which condition. And okay, so this is my delegate. And I then return, I intercept invocation, and then I pass it to my own class, which is not specific to ByteBuddy. It's not annotated like that and so on. So this is where my own code starts, and I'm not showing it here because it doesn't do anything very smart. It just like stores parameters and methods in some form, which I later can find when the call happens. You can look it on the GitHub. So what are some challenges and things that stand in the way? You can only mock method calls with this approach. Otherwise, it will be very hard and not easy to change bytecode for fields and so on. So it's doable, but I didn't want to go there, and none of the mocking frameworks are doing that at the moment. By the way, if you have any questions, just feel free to ask. So, for example, this one can be mocked because it's a method call. But this one is a field, and it's not supported. I think it can be done in Scala, but because in Scala it's different, Scala does it differently, and in the end it's still a method. Another thing is what I wanted, what most frameworks don't do, is to report if I specify a mock and that mock is a nonsense. So for example, I do not do anything with a mock, and I may consider that I set mock properly. So I want this command failed even before going into actual execution of the system under test. And it will throw a method. It will throw exception, which will explain what is going on. This is another thing that I wanted to do, reporting to be as precise as possible. Okay, so one thing that I would probably improve here, that currently it's strict order. It works most of the time, and maybe it's a a good way to debug your tests, debug your production code, but it implies some imperative knowledge about your code. So your tests hard code in things that happen in your production system. So currently it's strict order, but it's very easy to add something which doesn't care about the order. And verifying stubs is another story, but for example, if you want to have a stub which can be called multiple times, then such feature probably should also be added. But it depends. Like I think that most of the code that I write doesn't require those features at the moment. Okay, and reporting is something that should be first-class citizen in mocking framework, and I think this is the most important part, and I mainly copied it from JMock experience and added some of the corner cases that I experienced myself. By the way, JMock has a very strange naming strategy, which looks like if you name if you name your variables according to the class name, just by lowercasing first letter, it looks like JMock somehow knows about name of the variable, but it turns out that this is only a strategy inside JMock. And this looks very similar to what I have in JMock and in JInsist. So I was very much inspired. So where does it fit? Where does such approach fit? It doesn't fit to legacy code testing, because the idea behind my implementation was to make test feedback as important as possible, and it's very strict. So it works well with test-driven development. It works well with new code that you write. And another thing is that I wanted to have very simple framework, which turns out, to summarize this talk, that when I looked first into what Mockito does, or JMock does, it turns out that they have very large code base. Mockito has a lot of code, and JMock has a little bit less, maybe because it's less used compared to Mockito. But still, like I couldn't imagine that those frameworks have so much lines of code. And I think Java 8 features helped me a little bit to improve syntax, but still Lambda syntax in Java 8 is a bit verbose. Hopefully in the future underscore will solve some of those problems. And the main takeaway from this talk is that use existing tools, but you need to understand where are their limitations. And I think I spent too much time just debugging my software without having a proper tool which tells me what's going on in my code. And I want to say thank you, and do you have questions? It's time to wake up.
Just a small one, not really a question, but I want your opinion on integration tests.
So integration tests, like if you look into testable design idea, which ports and adapters, like something that you integrate with, like for example, database, you have to test only with integration tests, otherwise you're not sure if they...
So you wouldn't test mock a database call?
No. I would mock a protocol or interface which I own.
Can you talk a little bit about why you can only mock things you own?
The main idea is that if mock brings something that you create yourself, and mock is a contract that you describe yourself. If you don't control a thing that you're using in your code base, there is very little like point to mock it, because if something will change, your mock will be incorrect. If you have something that you control, you can at least be sure that you're using the way that you are that you were intending it to be used. That's the idea that don't trust third party. So that's the point. So, and mocking only helps with interface, or it doesn't guarantee that internals will change. So mocking works very nice inside your own domain, inside your own business logic, because you have at least tests for implementation, and then you have tests for the user of that class, which can then be injected with a mock.
So from third parties, you expect to get test kits, right, or something to test it with?
I'm not really sure if I'm a huge fan of test kits, because test kits may bring a coupling problem. I think what's really nice that what I want from third party is a good protocol. So you bring a well-defined API, it's clear, expressive, and then I can rely on you. Anyone else? So I think thanks.
Also a reminder to vote for the presentation in your app. Thank you.
Jason Voorhees. No, actually I don't need this mask. I am Nikita Lipsky, and today we will talk about JIT versus AOT. What a boring slide. That slide is much better. So meet for G team is Freddy Krueger, and for AOT team is Jason Voorhees from Friday 13. You know, all compilers are monsters. So every epic story should begin with once upon a time when C++ was cool and new, all compilers were static. C++ was compiled statically, Fortran was compiled statically, and even Pascal was compiled statically. Until into this world came Java. No, Java didn't invent dynamic compilation, but thanks to Java, dynamic compilation became a mainstream. So if we talk about Java, we implicitly mean a JVM and a Java bytecode that is executed on that JVM. And JVM can execute bytecode by two ways. It can interpret it, that is slow, or it can compile it down to machine code that will run directly on the underlying hardware. But there are also two moments in time when such compilation to native code can occur. Dynamic or just-in-time compilation occurs at application runtime, while static or ahead-of-time compilation occurs before program execution. Let's refer to the next slide. Here, above the dotted lines, you can see what happens before program execution. Underneath of the dotted lines, what happens at application runtime. On the left, you can see conventional JVM, such as the Oracle hotspot. What happens there? Your source files are translated into class files that are then put into jar files. And at runtime, classes from jar files are loaded by the JVM, and they're firstly interpreted by interpreter, and with the help of profiler, it is detected hot code that is fed to JIT compiler that produce native code that runs directly on underlying hardware. In the middle, you can see JVM with the ahead-of-time compiler. As you can see, all your class files are translated into machine code, into native executable, before program execution. So your application starts on the underlying hardware right from the start. In more general case, however, some classes can be unknown before application execution, such as third-party plugins and dynamic proxies. So even a JVM with a ahead-of-time compiler should be equipped with a just-in-time compiler or interpreter. What we are going to talk today. First, I would like to dispel common myths around Java ahead-of-time compilation. Then I will show you what challenges it actually has. And then we will talk about all dispute, what is better for performance, dynamic or static compilation. And finally, we will talk about application of dynamic and static compilation in various fields of use of Java. Client-side, server-side, embedded, IoT, and mobile. But first, let me introduce myself. For nearly 2 decades, I have been working on Excelsior Jet project. It is a complete JVM with a ahead-of-time compiler certified as Java compatible. And I have been working on this project. I worked on this project from the day one and contributed to all its components. On this slide, you can see a Java compatible sign. Actually, we sweated blood to get the sign. Some microsystems before and Oracle now do not give this sign to everybody. This sign in particular means that our implementation is Java compatible implementations. And thus static compilation is possible in full conformance with Java SE specification. And the next slide proves that it can be useful. It is our customers, only a few of them. Since inception of Java, numerous myths have been developed around Java static compilation. And I would like to start my presentation with dispelling those myths. And first myth is Java is too dynamic. It has the following features like reflection, dynamic class loading that make Java static compilation impossible by its nature. But let's look closer at those features. What is essentially is reflection? It is some metadata about your program. Class names, field names, method names. Nothing prevents static compiler to just put that data into data section of resulting executable to let runtime routines to use it to enable the reflection. In other words, reflection just works for statically compiled code. As to dynamic class loading, yes, a completely new class can appear at program execution. It can be downloaded from internet or generated by a framework. But I would like to point your attention to the fact that 99.9% of your classes are usually known before program execution. So nothing prevents you from compiling those 99.9% of classes statically and let remaining 1/10% of classes to be handled by dynamic compiler. So the dynamic class loading does not prevent you from compiling absolute majority of your application classes statically. The next myth is AOT kills the main Java principle. Vora, write once, run anywhere. But listen, this principle sounds like write once. It doesn't sound like build once. It means you can compile your application, or you can write your application once, build it for every target platform, and run it anywhere. Moreover, many desktop vendors already distribute their applications in platform-specific installer packages. And for those vendors, adding a static compiler is just an additional step in their build process. And if you're on the server side and use Docker, for instance, please note that Docker image is platform-specific as well. And the next myth is, if Java had a static compiler, it would transform into sort of C++. That is, if I have a 100 kilobyte jar file, I can transform into 100 kilobyte executable that I then can send to my friend that will execute it without having to install any Java. Okay, but Java comes with thousands of standard classes that any Java application can use. How they will appear on my friend's PC? And what about garbage collector, reflection? What I would like to say, both C and Java have runtimes. But C runtime is very small. It can only allocate and deallocate memory manually. And its standard library is also small, like stdlib, stdu. Java standard library is way bigger, and its runtime is much more sophisticated. But anyway, using a static compiler, you can compile your application classes along with standard classes and needed runtime support into one executable, but that executable won't be small. But it can be smaller than the whole Java runtime because static compiler can compile not all platform classes, but only those that are actually needed by your application. It can help to reduce installer packages in a great extent. Previously, I have been trying to convince you that Java dynamic class loading does not constitute any problems to Java static compilers. If I succeeded, congratulations. I have cheated on you. Actually, there is one feature in Java that causes a big headache to Java static compiler writers, and I'm talking about custom class loaders. In your application, you can create at any moment a custom class loader that will override standard class loader logic, and then class reference resolution in your application will function as you define. Why custom class loaders are used today? They are used in Java EE, where multiple web applications can be deployed into one web server, and to isolate them, they are loaded by separate class loaders. And they are used in dependency management frameworks like OSGI. And with all those modern frameworks, there are entire clusters of Java applications that have their majority of its classes known before execution, but unfortunately, all those classes are loaded by some custom class loaders. So how can we compile such applications statically? A compiler has no way to know how to resolve references in such applications between classes. And first, it can give up to resolve references and compile each class in isolation from others. It would work, but won't good performance because to make your application to perform fast, a compiler should resolve reference to enable inline substitution between classes. Fortunately, there is another solution, albeit partial. Actually, developers do not write their own class loaders. By the way, how many of you have ever written your own class loader? Okay, but usually developers don't write. They use ready-made frameworks that employ custom class loading logic internally. Thus, we can learn how class loaders work in those most popular frameworks and support them at the JVM level if they were standard class loaders. And I'm going to demonstrate you how to do that. Let's say we have an application that has majority of its classes known before execution. But unfortunately, all those classes are loaded by some custom class loaders. And first, the compiler should know how many and what type of class loaders will be created at runtime. How it can be done? By inspecting the structure of application. For instance, if we are dealing with Eclipse RCP, where each OSGI bundle is loaded by some custom class loader, we can scan plugins folder to know how many class loaders will be created at runtime. And then we should name those class loaders. It is known that several fully qualified, several classes with the same fully qualified name can be loaded into one JVM, provided that they're all loaded by separate class loaders. And in order to differentiate such classes, we need to add prefix to each class name with its static class loader identifier. So how can we name class loaders? For instance, if we deal with Eclipse RCP, where we can choose a plugin name for class loader unique identifier, which is unique in Eclipse RCP. And after we named class loaders, we should distribute application classes among the class loaders. And after that, we can resolve references both within each class loader and across class loader boundaries. But as you can imagine, compiling is just a half of the battle. We'll also need to load such classes at runtime. How can we do that? Let's imagine that at a certain moment, a certain class loader wants to load a certain class with a certain name. Sooner or later, it will inform about its desire the JVM, because class loaders cannot load classes themselves. They can only look up classes, delegate class loader requests to other class loaders, and ask the JVM to load a class it has just found. And at that moment, drawing on our knowledge how particular class loader works, we should derive that static unique identifier of class loader from its runtime instance. How can we do that? For instance, if we deal with Eclipse RCP again, we can find that where we named our class loaders by plugin names, we can find a plugin name in an instance field of a class loader instance. And then, if we have class loader name, class name, we can find that class in the executable and load it. But please note that loading of classes, of statically compiled classes, differs from loading them in a conventional JVM. All that we have to do is to create Java-Lang class instance and fill it with the reflection information. All class reference resolutions, verification were performed ahead of time, and code will be loaded by operating system. Talking about practical application of this theory, there is a support for Eclipse RCP and Tomcat class loaders in Excel Servjet. So yes, you can compile your Tomcat web application with all your frameworks such as Hibernate, Spring into executable, and it will work. And yes, you can compile Eclipse IDE statically. So we can claim that for any Java application that has a majority of its application classes and respective class loaders known before execution, we can build a static compiler that would effectively transform into native static executable. So is static compilation of Java applications possible? Yes, for sure. So ahead of time compilation of Java applications possible. But why do you need it? How it can be useful? Let's start from the obvious things. It is known that Java bytecode can be easily reverse engineered with the help of decompilers. Decompilers are free, easy to use, and produce amazingly readable source code, almost the same as original. And if you do not want to distribute your application in almost source form code, you would use a tool that would hinder reverse engineering process. And to-go solution for this problem is obfuscation, and its simplest form, name obfuscation. Name obfuscator replaces all class, field, method names with nonsense, so resulting decompiler output much harder to read. But name obfuscation has one big drawback. If your application uses reflection, or framework that you use uses reflection, you should supply an exclude list to your obfuscator, telling it to not change names that are accessed via reflection. It is a time-consuming task prone to errors. Moreover, what you would like to do with your application in the future? The most probably you will refactor it, renaming class, field, method names, and then you should renew your exclude list. If you forget to do that, everything can work on your development PC, but when you deploy it to end customers, everything can stop working at the most inappropriate moment, and you will even notice it at first sight. So why static compilation is better? First, there are none of tools that can translate native code back to Java source code. All that you can do with machine code is to disassemble it. But to read and understand disassembly requires from you much more qualifications than to read and understand Java source code produced by decompilers. Moreover, it is much harder to understand what the code does if there is no symbolic information attached to it. And after all that, optimizing transformations that can be applied to a code such as inline, specialization, resulting native code can only remotely resemble the original. Simply put, static compilers protect your code from reverse engineering into the same degree as it were written in C++ in the first place. Next comes the opinion that statically compiled applications should start, Java applications should start faster than on conventional JVM because there is no warm-up cycle involving profiling, interpretation, profiling, dynamic compilation. Is that true? Please, you probably noticed that big applications starts much slower for the first time than they start for the second time. It is true for any application, whether they've written in C, C++, or Java. It so happens because when you start your application for the first time, a lot of code and data should be loaded from the hard drive. On a restart, many of that code is already in disk caches, and your application starts much faster as a result. So what can AUT compiler can help us reducing startup time? Please note that native code actually thicker than Java bytecode due to its low-level nature. For instance, fetching an array element in Java bytecode is one instruction, while expressing the same instruction in native code will produce multiple instructions. So resulting native executable can be significantly bigger than the original jar file. Now recall that the most of the time during startup is spent in loading code and data from the disk. So everything that we won, eliminating the warm-up cycle, we lose because we need to load more code and data from the hard drive. And when we did our static compiler for the first time, it was a real surprise for us that startup improvements were not so significant. But we solved that problem. We do execution startup profiling, which is easy to automate. And during that profiling, we identify code that gets executed on startup. And then we place that startup segment into the beginning of the executable and preload it with sequential reading, which is much faster than random reading on a rotating media. And as a result, Java applications start really fast. For instance, here we compare startup times of 3 applications with similar functionality. All they are RSS readers. First 2 are Windows native applications written in DLL and C++. And third one is Java application. And third group of bars represents startup time of Java application running on conventional JVM, and fourth group of bars represent startup time of the same Java application running on a statically compiled. And as you can see, statically compiled Java application runs as fast, almost as fast as their native analogs, while the same Java application running on conventional JVM starts 2-3 times longer. So for this app, Java static compilation class clearly helped to reduce startup time. Next, let us consider performance. Actually, there are two opposite myths regarding performance in JIT versus AUT battle. And first myth is, if we, by compiling Java statically, we are making it equivalent to C. C is faster than Java, therefore, statically compiled Java is faster. So what is incorrect in the statement? Your guesses? Okay, yes, everything is incorrect in the statement. Actually, Java, unlike to C, C++, is managed language. What does it mean in practice? That when you dereference a null pointer or violate a bounds range, you will get null pointer exception or index out of bounds exception that you can catch. In C, you will get immediately a sigfold that you without any opportunity to recover. But this or that safety features of Java do not come for free. And they are not free both for static and dynamic compilers. But the statement that C is faster than Java is also incorrect. For instance, if you write your application in C, you will likely use some native libraries, and not all C compilers can use that native code to optimize your application. On the other hand, all library code is available both for dynamic and static compilers. So even even code from standard classes can be inlined into your application code, giving your application a significant performance boost. But there is also an opposite myth. Effective optimization of Java applications is only possible in the presence of its dynamic execution profile. This myth is the most difficult to bust because the best JVM engineers have been hammering this myth to Java developers' heads for years. But I would like to bust it anyway. So if we talk about performance, we talk about code optimizations. It is not enough to just translate your application to native code. To make your application perform fast, and numerous optimizing transformations should be applied to your code. On this slide, you can see only a few of such optimizing transformations. Please don't read this slide. Discussing all this optimization is far beyond the scope of this presentation. But I will tell you very briefly about optimizations that are especially critical for Java. So what we have in Java? It is common in Java to write programs in very good object-oriented style. We're using various design patterns, frameworks, best practices. So from a place where you need some functionality to a place where that functionality is actually implemented, the control is passed through a long chain of intermediate calls. So a good optimizing compiler should see that chain and inline it all to the caller method. But unfortunately, all calls in Java are virtual by default. So methods called virtualization becomes a very important optimization in Java because it's precondition for subsequent inline substitution. And method called virtualization can be based on the following three techniques: class hierarchy analysis, type inference analysis, and profile-guided optimizations. Let's consider them. The idea of class hierarchy analysis, or CHA, is very simple. We traverse class hierarchy, taking note of the methods that are not overridden. And if it's so, we can devirtualize such methods and call them directly. And dynamic compilers can even inline such methods unconditionally. In static compilers, but there is one drawback with this optimization. When a new class is loaded, that overrides such a method, it immediately invalidates all its inline substitutions. So dynamic compiler should throw away all affected code, de-optimize it, recompile, and so on. In static compilers, we can't do that. Instead, we insert a check that checks if a receiver object was the subject of CHA. If the check passes, we execute inline body of method foo, else we just call that method virtually. Please note that this check can be implemented quite efficiently with just one CPU instruction. But anyway, CHA has disadvantages both for dynamic and static compilers. Fortunately, there is another technique that often allows us to virtualize calls always, unconditionally. It is based on the fact that for newly created objects, all calls can be done directly, regardless if some classes of class A exist that override method foo or will be loaded later. Is it clear that for this code pattern we can call method directly? We know exactly statically know the exact class of that call. So we know the target method. So the idea of type inference analysis is to calculate instances of what classes are assigned to local variable A. And if it appears that all possible sources of such assignments is new operators on known set of classes and method foo is the same in all those classes, we can call method directly again and optionally inline it. But code pattern where we assign new operators to a local variable is not very often. Moreover, we have some other calls that are assigned, the result of them are assigned to a local variable A. So how can we virtualize call in that case? Let's suppose that we know that method bar always returns instances of class B, and method bus only returns instances of class C. And in that case, we can call method directly again, but this poses the question, how do we know what bar and bus return? And here we can enjoy something that none of dynamic compilers can even dream of. A static compiler can use within reason as much time and memory for optimizing your application as it needs. For instance, it can scan all methods of your program prior to optimizations and compute some useful information about each. For instance, it can compute instances of what classes are returned from concrete methods. In starting our analysis from a list methods that do not call anything up to call hierarchy, we can compute such information quite efficiently. And thus, information what methods bar and bus return often becomes available. And the analysis that analyze all methods of your program is called global analysis. What else it can be used for? How about detecting if a method parameter is not escaped into shared memory? This information can be used in escape analysis that determines whether a locally created object escapes from the method stack frame into shared memory. If it appears that it doesn't escape, it can be allocated on a stack rather than a heap. Escape analysis local escape analysis cannot detect such objects if object is passed as a parameter to other methods. Probably you know that hotspot does escape an allocation, but optimization. But in order to do that, it should inline all methods where to which subject for stack allocation is passed as a parameter. But it is not always possible to inline such methods. Hopefully, with the help of global analysis, it is not needed to, often it is not needed to know about it, because we know if a parameter is escaped into shared memory or not. And I'm going to demonstrate you how it all works together. Let's say we have a pretty frequent coded pattern, iteration over collection. First, Java C compiler will actually desugar this into a code that's similar to the following code. We get iterator from collection, and with the help of has, next, and next methods, do iteration over a collection. How can we optimize such a frequent code pattern? Please note that has, next, and next methods are abstract, so we know nothing about them in general case. But what if we have some bits of information from global analysis? Let's say global analysis has shown us that get collection always return an array list instance. And things suddenly become much better, because we know everything about array list. And for instance, we know what iterator method does in that class. And if we inline it, we see that iterator becomes not an abstract iterator, but a concrete iterator. And we know everything about this iterator. For instance, we know that in its has, next, and next methods, iterator object is not escaped. So we can allocate that object on the stack, and if we inline constructor, we can see its fields. And then we can inline has, next, and next methods, and what we see that iterator object is not used as iterator anymore. It is used as a set of fields. So we can transform into local method variables. And what we see now? We see that it is simple for with a counter. Its inductive variable was an instance field of unknown object before the optimization. And now it can be allocated on a register. The loop can be versioned. All runtime checks can be removed from the fast version. We can inline do something, move all its loop invariants out of the loop. And finally, we will get the most effective code for this quite pretty code pattern. And I would like to emphasize that we did all that amazing tricks based on only on the results of a static analysis, without executing that code any single time. So, concluding my talk about performance, I would like to say that optimizations, analysis, and respective internal representation can be quite sophisticated and require a lot of computational resources. And as you have just seen, it is not enough to perform optimization only once, because some optimization can give opportunity to other optimizations. So ideally, you should repeat them until reaching a fixed point. And global analysis actually depends on the whole program. So a volume information it produces depends on the whole linearly on the whole program. And in our static compiler, for instance, we store results of global analysis on the hard drive because it does not fit into RAM. So finally the question is, can a JIT compiler afford all of that? It shares CPU and memory with your application. And if first 2 points are arguable, I can say for sure that global analysis is not for dynamic compilers. Really, can you imagine that dynamic compiler will use gigabytes of disk space to optimize your application? But what dynamic compilers are good for? First, it can compile not all code of your application, but only those that are actually executed. And it is the main advantage of dynamic compilers, actually. From our experiments we performed several times, profile-guided optimization do not give much performance, but it is enough to compile hundreds less of code to achieve acceptable, than static compilers to achieve acceptable performance. And this observation makes dynamic compilation at all possible. And then the dynamic compiler can devirtualize calls not based not on a static analysis, but on actual execution profile. So if it sees that at a certain call site the target method was always the same, it can assume that it will be the same the next time and in the future and inline it. And extrapolating the technique, it can see hot execution traces in your program, row them in basic blocks, and optimize very aggressively. It works and works very well. But I would like to ask you, what happens when an app has no distantly hot code running on a conventional JVM? It often holds, for instance, for UI-centric application, when you have many code for menus, windows, event handlers, and so on. And all that code is executed not frequently enough on a conventional JVM to justify its JIT compilation. So that code is simply interpreted on a conventional JVM. And it, of course, influences user perception of the application. For instance, if we present the same application running on conventional JVM and statically compiled to a user, he will not notice a difference for the first time, but after working on in that application for several times, he will note that statically compiled application responds to its input faster. So static compilation works better for UI-centric application because it compiles every single method of a program, applying the most aggressive optimization as possible. And the difference can be demonstrated on the following slide. Here we compare, it is a chart showing JFC mark benchmark. It is a benchmark that we created several years ago to measure UI responsiveness. It takes a 7set2 demo from JDK and manipulates it with help of robot. Open closes windows, model dialogues, scrolls down rich text control, and so on. And the benchmark has two modes. Short run is indicative when you just run your UI application, and long run when you use it for several hours, for instance. And here the performance of Excelsior Jet, hotspot client, hotspot server are compared. As you can see, in a short run, statically compiled applications runs 2 times faster than hotspot client. And in the long run, hotspot becomes faster, but it is still 1.5 slower than statically compiled code. But you may ask, who writes client-side software in Java nowadays? All we have server-side, and on server-side, dynamic approach works better, of course. But I would like to ask you, can a static compiler use dynamic execution profile as input? And the answer is yes, of course. Actually, all modern C compilers implement profile-guided optimizations. But it can be not so convenient to feed static compiler with a profiler for UI-centric application every time you need to rebuild your application. But as you can remember, everything is more or less good for UI-centric application with and without execution profile. But when we move on the server side, we can know that after working on a high load generated by real users, application execution profile will likely stabilize. No new classes will be loaded, and JIT compiler sits idle. And what if we, at that moment, send an actual execution profile to another server, where static compiler installed and won't having relaxed memory time constraints and having an actual execution profile, it can transform your application, it can optimize the application in the most effective way. And this scenario, I believe, is the exact scenario where static compilation can be beneficial on the server side on the server side. Moreover, we at Excelsior already have some satisfied users on the server side. Some of them benefit that the performance of statically compiled applications is stable. There is no de-optimizations that can occur at unknown time, so latency latency much more predictable. And some of them benefit for better startup time, which is 2-3 times better than for conventional JVM, and it can be important for when you need to run a bunch of microservices simultaneously. And when statically compiled servers start, it works as the same as other servers in the cluster, so load balancing does not suffer. Let's now move to another side of the spectrum, to embedded Java. To an outsider, it may appear that if time has stopped in embedded world, processors are years behind those that are used in today's desktop and server computers, and other computational resources such as random access memory are often scarce. Now, the weaker the hardware is, the more expensive dynamic compilation becomes. Resource constraints simply don't let dynamic compilers to work in full force. So for embedded systems, static compiler is just the ticket. Little known fact that some microsystems before and Oracle now always included static compilers in their Java ME offerings. And somewhere between desktop and embedded worlds lays beautiful world of mobile devices. Let's now think how JVM can look on mobile platform. First, it of course needs platform classes, memory manager and GC. Reflection can work without reflection, but I would rather say not. JIT compiler. What's missing? The charger. All that modern mobile devices have a battery. Is it worth to spend battery on every application start that can be reused later? So probably it is it was the reason why Steve Jobs prohibited any dynamic compilation on iOS. It leaves static compilation as the only viable alternative on iOS. What static compilers actually exist? At the turn of century, it was a half of dozen of them, but only 2 have survived. It is Excelsior Jet and GCG. But GCG was not evolved several years, and it is finally died this year. And with iOS appearance, we can observe a new Java static compilation boom. All wants to bring Java to iOS, and there are several solutions. Until this year, the most famous was RoboVM, but then it was acquired by Xamarin. Xamarin was acquired by Microsoft that decided to kill RoboVM. But you can use multi-auth engine now. It exists for iOS as well. And you know that Android has ART, that is also static compiler for Java. But all those solutions are used Android class libraries, so they are not Java compatible. And as I said, Oracle always had static compilers for their Java ME offerings. IBM has static compiler for Java SE embedded. And we cover, at Excelsior, we cover desktop servers and embedded. And we are going to move to mobile as well. And we believe that our solution will be Java compatible on mobile platforms. And probably you have heard that ahead of time compiler will finally appear in Java 9 as well. in hotspot and OpenJDK under the JEP 295. So Oracle always tried to convince that static compilers for Java are not needed, but now it seems they have changed their mind. So let's sum up. So today you have learned that static compilation of Java applications is possible while preserving all Java features, and it can be useful. It can be useful for overall user experience, tamper resistance, protecting your application from reverse engineering, better stop time, etc., etc. But anyway, JIT and IoT have their unique advantages. So I believe that synthesis of those two approaches will bring us the maximum benefits in terms of performance. So thank you very much for attention. Your questions, and I have some T-shirts for questions. Huh? 2 slides back, okay.
Raise up your hand.
Another one?
When Java crashes, it produces stack trace. When code is statically compiled, what it produces?
It produces stack trace because if we talk about our implementation, which is Java compatible, we have to produce Java stack trace, of course. And it works. Every single Java feature works for statically compiled code, at least for our implementation. And you have a T-shirt. What else?
Which versions of Java do you support, and which target platforms do you support?
We support now Java 8, Windows, Linux, macOS for x86 and AMD 164, and ARM, Linux ARM 32 for our Java embedded solution. Okay, you will also have
dangerous sitting here.
Some other questions?
Does your compiler only works for Java or for all JVM languages?
Of course, it works for all JVM languages because we transform into native code Java bytecode. So any JVM language that is translated into Java bytecode, we can compile statically.
Thank you.
About it. Another questions?
Thanks a lot, Nikita.
Thank you for your attending.
Please leave your vote for the talk in the in the mobile app, and here will be closing notes. So don't leave the room.